of the cases, whatever you are discussing, these all would be covered. So I'll just show like what kind of robots we do work. So we do work on conventional locomotion and as well as conventional control. Apart from that, we do work with non-conventional. So where I explore different scenarios. So for example, you would have seen that the legged wheel, or you can say weg wheel, or you can see like underwater vehicle, or even you can actually see that you can say the terrain, all-terrain vehicle, which is mainly for agriculture purpose, or it can be agriculture or arm defense related. The same way you can see like we do work on assistive, specifically on rehabilitation. This is the very first prototype we made for lower limb rehabilitation. I want to show because it is part of IIT Indore career. So this is the very first primitive prototype we made. After that, we have improved and then even we have transferred to one of the Russian industry. So apart from that, you would have seen that, so few other direction also we do work. So you can see like hybrid drone also we jointly work. And, along with me, so Professor Ash. Now you can see that I cover from service to assistive robots. So that means you can see like some kind of mechanical point of the robotics I start covering. And I'm also like a strong believer that Indian economy is always depend on the product oriented. So I encourage my students to work towards product. So these are few of our BTech students who eventually contribute to a product development. So these are few of our products related thing. So now coming to the topic which I'm going to talk about, marine robots. So you know, right, so 70% of our earth is actually like covered of water. When we talk about space or ground, we have lots of explorations. And we have achieved also certain level of autonomy. Even I'm not saying achievement of just robotics, even autonomy. But when you talk about underwater, we have limitations. So what kind of limitations we have? So there are a bigger concern. So that is the way we are actually like discussing. So you can see like the human cannot actually like see after certain depth. So which actually like make very, very critical. So the human drivers or cannot be directly deployed. So even you put a human occupied vehicle, which is what the Deep Ocean mission has launched as a HOV. So even that actually like having a huge investment. And if you look at it in the recent trend, how the world is moving, even China is actually like a planning to install a, you call how the space station is there, the same way they want to install a underwater station. So where they want to actually like a plan to have the human people, at least 14 scientists, they want to put it in 2030 at 2-kilometer depth, 2000 meter depth. So they want to make a station. So that means they were actually like seeing that there is a potential in underwater. They want to try to establish. When you see that, what the limitation, not only the depth visibility, the pressure, and as well as the risk of life. So these all actually like making that the robot can, or the machines can help us to go deeper. So that's the way you can see the robots have start coming. And the idea is actually like the machine, or you call the robot in later part, is not a new thing. So even you would have seen the Da Vinci started with the human occupied cell, or even he tried to actually like come up with unmanned cell with some kind of string or you call cable. So this is what the idea, but that idea is still evolving. We are actually like keep getting matured. So that is what I try to bring it. So that means if you look at it, the bigger picture is, so we are trying to see the ocean for two purposes. One is try to actually like do some interventions. For example, I want to install underwater, you can see structures or underwater pipes or underwater cables. So you would have know that most of the internet cables are coming through, you call the ocean. And as well as several countries try to bring even certain important element also through pipelines. So that means you can see like that is one part where you want actually like install those things. The second part to inspect that. So this is one part where the commercialization side. The other side where you want to actually like understand how the earth is actually like getting affected by different source. That also you can actually like sense from the ocean. So that means you can actually like use this as a one of the observation medium where you can actually like do it. So apart from that, so people now trying to find wherever the resources are available. So in that sense, people identify that. So ocean also another source where abundant minerals and as well as the important ingredients which we are talking about AI, that also people thought that it would be available, so trying to explore. That means you can see that the ocean is actually like playing not only for the commercial purpose, so even to help the commercial purpose also the ocean is there. That means you can see like you can actually like do multiple aspect. So the bigger picture is ocean is like a really abundant, how 70% of earth is covered. The same way lots of opportunities were there in the ocean. So when you look at it, so there are two ways we can actually like explore. So one is you can actually like make it a remote sensing. For example, you put it multiple beacons, or you can use a satellite or some other mode of, you can say put a remote sensing. This is one way. The other way you can do it in situ. So that means you can actually like explore lively. So when you see exploring lively, then you want a platform which will be moving. So that is the part we are trying to bring it. So that means you can see that the underwater vehicle is actually like one of the critical part. When you see underwater vehicle, there are two classes of underwater vehicle we used to work. So one is for intervention purpose, the other one is for inspection or observation purpose. So these vehicles I will not cover here because it is actually put it up outside. So where the TDF 3 and 4 is covering both vehicles. So these are actually like a part of our research. So I'll just skip these things. So where we have come up with a rectangular prism with or 4 thruster, rotatable 4 thrusters. These are available outside. So I'll not spend much time on this because I have a limited time. So when you come the same way, the bio-inspired also like taken further. So there are several ideology we brought in and found that finally the box face is actually like one of the best one from our understanding and the literature. So then we try to mimic the you can say the bio-inspired box face as an underwater vehicle. Then we come up with a vehicle, and this vehicle also available in the, you can say, exposition. So you can actually like try to see and get more inputs. So where Dr. Jagdish also, our collaborator, he has put a stall here. So now the same way we have another joint project with IIT Guwahati Hub. So where the ship hull cleaning, this is also available there. I'll not, you can say, discuss these things. We'll come back where we are actually like leading. Why this particular topic is actually like important, where we said the human-robot collaboration in marine robotics. So the bigger issue is the demanding part is, so you don't have actually the visibility. That is one critical thing. The second thing is actually how to overcome the pressure when you go deeper and deeper. So when you see that, one of the critical part which I want to start with, so we all know like the industry 3.0 evolved to make it automated plants. So that means the semiconductor industry boomed where the automation has come. When the automation has come, the robot also came. But what really the inspired thing, people try to mimic how the human used to do, the same mimicking they want to do it, but that particular time they could not do it. So what they did instead of that, they want to have both mobility and manipulability, they try to cut it. So they cut the parts apart. So the upper body, which is actually like fixed to one base and considered as a manipulator, it will be doing only manipulation. So where the lower body, they cut it and they assume that it's a mobile base. So initial days, they started with AGVs. So automated guided vehicle, where the tape or probably the guided rail would be there, so it follow. So why this all happened? Because that time, you call the sensor localization, or you can say sensor integrated localization is not that easy. And as well as the probabilistic robotics were keep evolving. So that's the part they divide into two parts. And you would have seen that industry 3.0 where the industrial manipulator ruled almost entire thing. When you see the same line, when you look at it automation, so the automation initially started with computer process control. Even though we say computer process control, it can be a PLC or a simple microcontroller. There are 2 points they try to mimic. The first one is actual process monitoring. So they actually like use of sensor, and it will give a, you can say, display to the human machine interface so that, okay, this is what happened, what you want to do. So you can actually like do it. So this is the way the first automation itself brought in. The second part is the process control. The same way, when you look at it, so the human, how they were actually like working, the same thing we want to mimic in every domain. So that means if you look at it in underwater, So there is a critical part. So how the human is having a dexterity, that dexterity we want to give. For example, I have a vehicle just for inspection is not bigger issue. But the point I bring it to intervention class, I want actually, like you can say, for example, weld the underwater pipeline. So my manipulator should be actually like proper dexterous. But if you look at it, the human, you can say dexterity is very good. And similar way, for example, I want to actually like even pick this object when it is down. I ask the manipulator to pick. I have to do lots of learning algorithm. But if I ask the human being to lift, easily he can do. That means we can use the human intelligence and put it in the loop where the machine can actually like reach this point and manipulate with the help of the human being. This is the way the initial underwater robot started. So where we call remotely operated vehicle. So the command they will give, once they reach the station, so the operator take hold and then he will operate. This is the way the underwater vehicle itself evolved. So that means when you look at it, the intervention class of underwater vehicle, so already the human in the loop and human collaboration was there. So that is what I try to bring it. So when you bring it, so lots of limitations which push the human should come. So that is what I put it. The sensor fusion failure can happen. The communication is only acoustic. So that means I have to plan for a wired or cable or tether. So these all actually like making me by default, okay, I will do the human intervention. So that's the part. So when you see the human robot collaboration, so what we are really looking at, so there are two advantages. The robot can actually like do its own, and whenever required, I can actually like play. So this is you would have seen in any industry. So the industry revolution also happened. So initially the robot or the machine will support. So for example, I said the industry 3.0 where brought the automation, the sensor will give the identification. So this is what happened. The manual operator will do decision. Okay, this has happened 10 objects. I want 10, it is done. Okay, I stop. Okay, now this is actually required to process. I'll operate this. So that is what the human machine interface pop up. So the same way, initially people thought that the robot can do certain extent and I can actually like support. But what happened later part, so how the industry also modified, so there was a supervisor. The supervisor knows everything, but he won't play. Whenever there is a difficulty, he will actually like play, hey, you do this way, you correct this way. So the same way we were actually like started the robot collaboration, even in an underwater. So what we are looking is a shared autonomy, and finally we give kind of human in the loop in autonomy. That means human would be only team leader, and he will actually like oversee that. So that aspect we were actually trying. So that means you can see that the robot's supposed to listen and as well as perform accordingly. So that means you can see like we were actually like looking for a human-friendly interfaces. So then we were actually thinking about the additional thing is the teleoperation become even remote operation. So here, so I'm saying the remote operation is not only wired. So here actually like bit of autonomy is bring into a play. And the third important thing is the feeling. So the feeling is very important. So when I'm actually like lifting an object in a ground, in underwater, and what kind of object I have to feel. When I am an operator sitting in a mothership, which is actually like 200, 300 meter, you can say far away, I cannot actually like feel it. Even the latency would be there. So probably it may be the latency in microseconds to even a second, sometime even a minute. So then I have to feel like this is what I picked. So that I have to bring it. So that means I have to see that the feedback in my hand or the haptic feeling supposed to be required. So if you put that way, the key aspect of human-robot collaboration in marine robot, I put it in 3 bigger cases. So where the mission control and shared autonomy can be one bigger concern, where this will work in a twofold. The human will give a strategy and robot will actually like work in a lower level. So this is what I want to cover. Okay, this is the profile I give as a human and the robot will do. But when we are doing the second part, the human-robot collaboration, the two underwater collaboration, where you can see that the gesture can be actually like recognized, or it can be actually like you can give some cues, so then it can actually like do it, or you can actually like see that the display signal with the help of some signal. So either it can be light or some display, you can actually like make it, so that you can actually like make this interaction enable. But we were actually like talking in aerial, the swarm, or you can say multiple agents. So that same thing we want to actually like make it in specific. So for example, larger installation in underwater or in a defense perspective. So where you want human swarm collaborations, or you can say multiple robot or heterogeneous robots need to be actually like collaborate. So that time actually like this human swarm collaboration would be beneficial. So even there are group of robot, but human can actually like take a leader role and he can command. How in the old war field, the bishop will actually like command, the same way this human operator will command, and the other robot having a communication either wired or acoustic basis. So that means actually like the communication is very, very restrictive. So when you look at it, this a bigger concern, there are multi other bigger concerns also there. The environment is actually like not like a calm one. For example, you take a lake and the sea will be having multiple states. So based on your, you can say the climate, the sea state also keep changing. So that means you can see the environmental is most of the time unpredictable. So in that location or in that particular perspective, how the human robot would be collaborate. That is a bigger part where we are still, people are trying to bring it how it can be achieved. So finally the robot is actually like far away from, you can say, the operator. Sometime actually like operator and the robot would be opposite each other, but the trust and the safety. So these are the bigger concern. So which we need to actually like bring it. So if it is a ground, you can actually like put the press button immediately. But when you are swimming and your robot is coming, which is actually like a try to penetrate you by a wrong command, so how will you actually like stop? It is actually a very tricky one. So that is where we were actually like trying to see the trust under the thing. So if you put that way, the human would be actually like playing multiple role in each and every aspect. But the weakness of the human role is actually the endurance is limited, because he cannot go, you can say, underwater for a longer time. And the environment sometime actually like even in a seashore, the environment may be risky. So that's what you would have seen. For example, you go to a seashore, some part of our regions, so you can see the starfish would be there. The starfish is actually like very vulnerable for a human one. Not only it is taking the, you can say, the creatures, even it is harmful for the human being. So that kind of issues will come. That means the human will be having a limited endurance and risk exposure is there. So then we can actually like adapt the robot. But when you adapt the robot, so the adaptability is limited and communication issues are there. So now this as a critical thing, this can be overcome by the implementation of AI. That is what I try to bring it. So now you can see that the AI is actually like in marine robotics, mainly to overcome these both limitations. Both human role and as well as the robot role can be actually like overcome with the help of AI. So that actually like bring it. So now you can see that the human contribution will give definitely in a safer working environment, because human in or on the loop, or human as a team leader. So that means the strategy and execution part would be monitored, supervised, and even sometime command by the human operator. So that is actually like human side. The AI will actually take care of the other part. We envision. That is what we are trying. So if that is the case, you can see that the AI assisted, you can say, marine robot collaboration will give larger picture. The larger picture will be having multifold. So what we are looking for, the designated autonomy, the robot execute and human approves. So this level we want to bring it. So for that we are actually like trying for everything. So if you put that way, so the human will demonstrate and finally the autonomy would be validated through sequence of process. So if you put this, you can see that there are multiple avenues where immediately we can try to implement AI-driven, you can say, the mobile robot collaboration with the human. So one is actually like, this will give a bigger picture, the situational awareness. So since we have put AI in the loop, so the AI will give a very good awareness model, so that make actually like a better, and it will give a strong perception model. when you give a strong perception, what additional avenue we can bring it, the intelligent decision control we can bring it. So when you see that intelligent decision, so then we can actually like definitely achieve what level of autonomy we want to do it. So this is what we thought the premier avenues which we were seeing. Apart from that, what we can see additionally, we can enhance the human-robot collaboration if we apply AI. So that make better, you can say, picture in the robot collaboration. And as we said, so the multiple robot or the swarm coordination we want, if AI is in the loop, so then that can be achieved better. Apart from that, the AI can give a trigger. So when the machine can fail, that condition monitoring also we can loop it. So in that sense, you can see that it can be used for preventive maintenance, and as well as we can see when the system will give energy efficient, what situation it can be performed better. These all we can actually like play. So that way we can see that the avenue even for preventive maintenance or energy efficiency aspect also we can work on. So that's the idea which we thought it. When you put these all, so there are several hurdles, several people try to overcome and do research on this. The very first important thing is the sensor grounding. So that is very important because the operator would be in a mothership or in a station. So he will actually like feel the sensor. So that's what we call sensor grounding. So this, how you can actually like feel it. So the sensor is actually like proper or not, that we need to be known. And similarly, he's there in the ground. So that real-time sensor is actually like we need to feel. So that aspect we are actually like trying to bring it from AI. So this is one point of research people are working. Several papers were coming into that aspect. So whereas lots of people have approached in the other aspect, which is actually like underwater manipulation autonomy. But if you look at it in the middle, so the other aspects are all common. So environmental, ethical, legal, these all are actually common for any AI-driven implementations. So that is what we are actually like trying to see. So if that's the case, so what we can see, like we will have enhanced human capability because AI is enabled, and we will see that diver who's actually like doing usually the task, so his safety is actually like improved. And you can see that the cognitive is very, very burden in the earlier days, but if you put it to AI, the human-robot collaboration would be improved. That means reduced cognitive burden will be there. And the important element is the multiple tasks and complex tasks can be achieved by implementation of these. So that is the idea which I put. As I already told, I'll just give only the layout, so where we can actually like play. So with that, I conclude my talk. So thank you for listening to me. So I'm actually like not AI expert, again I'm insisting. So I'm actually like seeing that as a marine robotics guy or a mechanical robotics guy, I want to see these areas can be collaborated by any of the AI or probably intelligent control people, so which can be play a major role, because now every field is interdisciplinary or multidisciplinary. So some of the expertise can be combined and can be executed. That is the part I thought of putting it. So that's why I did not go through any of my research in detail. I tried to give a essence of this. Thank you. Yeah.
Thank you, sir. Thank you for this nice talk. We can have one question. Yes.
Thank you, Santa Mohan, for your nice lecture. I have one question. What is the maximum depth to which you reached with respect to your underwater bot?
So our vehicle is limited to 300-meter depth. The vehicle which I worked with NSTL, it can go up to 600-meter depth. The collaboration work which I work with NIOT, it can go up to 6 kilometers.
Okay. Because one of the things which I personally feel is that as you go on increasing the depth to which you can reach to with your boat, the hydrostatic pressure will become more and more, and therefore you really need to tweak around with respect to the material of the boat to deal with the lateral pressure. So your thickness keep increasing and your features keep increasing. So that's why it is heavy and as well as cost expensive system. So we do anticipate this. Another thing I was wondering is that did you think of some short wavelength electromagnetic wave-based communication for communicating with the bot?
So there was one attempt in our lab. So not only acoustic, so they tried electromagnetic wave, but these all limited.
Of low wavelength range.
That's what. So there are limited depth it can go, but still this point people are trying to go across. So even optical has a diffraction, so
Yeah.
we cannot go that way. So that's why we are relying on either camera
Ultrasonic
or
waves.
acoustics. That's what we are depending. But several line people are attempting this aspect. Even my former group in Korea, they do work on this aspect.
But ultrasonic based communication works reasonably well underwater, because currently that's also the state of the art practice for detecting a school of fish
Yes,
in the ocean, for particularly used by these trawlers to detect where the school of fish is and for fishing purposes. So that's also, I mean.
So in fact, I want to say here, so there is a, you can say NPOL in Kochi. So they were actually like a DRDO lab. They reached almost like world-class level sonar development. So we are having a good, you can say, facility to develop this kind of sonars. So what kind of sonar you want, forward-looking, or you can say multi-beam sonar, or dedicated sonar for navigation, everything is actually like in-house making it. So that way we are matured in sonar side. But what you said, the alternate, we don't have it. People are working on. Even NPOL themselves is actually like working with multiple level, even fiber optic combined with acoustic, like that. They were actually like playing multiple play. So people can think about that. Yeah,
Thank you.
So nice overview of human-robot collaboration in marine robotics. I'm just wondering, when you are talking about AI assistance or using AI for some of the challenges, are you trying to also build some simulation platforms where you can train these models or collect data? Because I believe that it is a complex environment where sensor behaviors may also change. So are you trying to develop something, or is there any existing where
No, there are some existing, and we do develop a, you can say, underwater robotics toolbox kind of thing in MATLAB and Python. So apart from that, there are some simulators. For example, even ROS, we have a UV simulator. So even ROS2 also similar alternate packages were there. So even some of the custom made platforms are already available there as a UIDF or SDF. You can actually call and try. And the environment also you can create. So that way, there are some platforms are available. So apart from that, some labs are having their own dedicated things. For example, Fossen Lab, who's, you can say, wrote a book on guidance and control of ocean vehicle in '94. He also developed very recently, I think 2 years back, he developed, along with UV simulator, he also developed his own package, which is open source, but it is useful for the underwater simulator, along with the algorithm experiments. So that way you can actually like use. Those platforms are available.
Can they also model such high turbulences?
Yes, that's what I'm saying. So the environment you can create. So that is fine. Yeah.
Thank you.
Yeah.
Okay, now
Yes.
we have to stop questions
Yeah,
here.
thank you.
They can write to you, discuss
Yes.
with you
So
later
that's
on.
fine.
Okay.
Yeah. Thank you.
So thank you, sir. Can we have a big round of applause for him? So please be here for 1 minute. So I'll call Professor Subhajit Rai Chaudhary so that we can felicitate him. Professor Subhajit Rai Chaudhary is our project director here at iHUB. And no, he's not Dean R&D, but he's heading HCi here. And he's our senior colleague at School of Computing and Electrical Engineering. Thank you.
Oh, when Vijay was there, so you made the project. So data science, sorry.
Now moving ahead, I would like to call upon Dr. Samrat Datta, who is a research scientist at TCS Research specializing in practical and scalable AI solutions for robotic automation. His background spans in imitation learning, reinforcement learning based robot control, and data driven manipulation strategies, supported by a PhD from IIT Kanpur, where he developed advanced learning frameworks such as dynamic movement primitives and GMR based stable movement primitives. Kindly come on stage, sir.
Good morning, everybody. Thank you for the nice introduction. Today, I will talk about how we can scale intelligence given the planetary boundaries. Well, imagine that you are instructing your robot, put the fragile items away from and clean the table. So for the robot, it will be wondering that what is fragile here, or what does fragile mean, or maybe where is away. But if I tell you to do that, it's quite easy for you. That means we need to break down the entire instruction down to the robot's level, where the robot can relate each and every action which is given in the natural instruction that can be mapped to the robot action space. So this problem, once this AI models have been invented, has taken three main directions. One direction, the model simply generated the code for the actions given the long horizon instructions. In the second direction, you use the model to break down the entered instruction in smaller chunks, and that chunks are essentially mapped to the primitive skills of the robot, and the skills are executed sequentially. And in the third aspect, the instruction is directly mapped to the action space. Now, we have seen if we increase the number of parameters of the model, the reasoning of the model increases. Okay? And as per this law, if we see that the number of parameters increases, the loss also decreases. But everything comes with a cost. Here also, if we scale in that way, eventually there would be some point where we'll keep on increasing the parameter, but the training will not be efficient. The loss will eventually not be decreasing, rather it will be increasing. So that is the point of sustainability, where we also call the sustainability tension point. If we see the sustainability picture, here you see if we are using a cloud-based LLM or VLM interface. So per decision, especially for the VLM models, it will increase if we use a model kind of ChatGPT or Gemini. That will be at least 10 times bigger than these numbers. So for per decision, it will take around 0.002 to 0.02 watts. And if we scale it to million robots, which are always connected to the network, that goes to 2 to 20 megawatts per hour for million robots. At the same time, if we can use our chat-based, our age-based models, we can see that this energy requirements reduces by almost 10 times. So sustainable robotics requires efficient and local intelligence, not just bigger models. So we have to ensure that intelligence can be captured or can be learned through these smaller models. So the open question is, what is the minimal representation capacity required for the robust embodying reasoning? Well, if we see that how the humans perform complex tasks, number of neurons in a human brain would be around 80 to 100 billion, and our average lifespan is 75 to 80 years. So through this duration, we keep learning. And if we compare it with the, suppose for GPT 3.3, or I guess 3.5, so it has a parameter of 175 billion, amount of data required is 300 billion, and if we train it using a single GPU, it would take around 355 years approximately. So is it really easy to bring this kind of understanding into a smaller model? Well, nature has an answer. This is a mice. Its brain is of about 70 million neurons, and it has an average lifespan of 12 to 18 months. If we can reward it correctly, it can learn what the humans were doing. Well, of course, it will not be a generalized learning, but it can learn domain-specific tasks. So this gives us the motivation that if we can train our model such a way that the rewards are given efficiently and specifically rewards are given, then we can also learn domain-specific tasks. So what we need to have such a robot which can actually translate human-level instructions to its core understanding and execute the tasks. So to do that, we need robots that can understand the intent of the user or the co-worker, and to do that, so it should be able to understand the instruction in natural language or simply the intent of the user. It should be self-aware. Based on the above understanding, the robot should be able to generate plan from the long horizon instruction. So it would require decomposition of the entire instruction, and it should be able to estimate the success of this primitive task sequence, and it should be able to learn the skills quite easily from maybe from humans from demonstration, or it should be adapting to the changes in the environment. It should be curious enough to learn or understand what is happening around. So we have formulated this kind of framework where we have various sensory inputs and language instructions. We have perception models separately, and we ground the language instruction to the level of the robots, and we have a language reasoner. So we make a soup of all these embeddings and the features what we extract from the input space. We mix it here with the visual reasoner and action simulator, and the executioner actually takes the skills from the primitive skill repository and executes it. So that is the overall picture. That is how we create the entire pipeline. And to do that, in a broad sense, we need this the 5 components, where we have the supervisory planner at the center. We need to have a perception stack. We need to understand whether it's within the distribution data or out of distribution data. We need a grasping model that can efficiently grasp the objects. And we need the skill repository, which are learned from various modes. To describe, now let us see how these individual modules can be learned. For the skill learning part, we have used imitation learning, then reinforcement learning with skill transfer, also the meta learning to incorporate the new skills into the skill repository. So in imitation learning, what you essentially do, that how the human children learned during their early ages by looking at their peers, by mimicking them. The same strategy we are following in the imitation learning setup. Now, we have developed this kind of framework where we have tried to mimic the video-based demonstration, and we wanted to understand the skills which the robot can perform. So there we have proposed one model that could understand the visual, the images that we give to the model. The model was essentially extracting the core areas where the task was actually happening. So this was an attention-based mechanism for which we used for the feature extraction. And the feature, when the feature was extracted, we used it for reinforcement learning, and the reinforcement learning framework learned the task actually. So here you see that one robot is mimicking another robot, the left side. The left side one. So here the right side robot is actually the teacher one, and the left side robot is the mimicking the right side one. And here the meta learning framework, where we are incorporating new skills into the existing framework. So here various tasks like pushing, pulling, etc. This kind of tasks are learned through meta learning. So if we implement this in a real life scenario, so that would look like this, where we are actually, the robot is performing stacking task here. The task is that there will be boxes will be coming in the conveyor belt. Here the conveyor belt is not there, it's a static scenario, but the overall the problem statement remains same. The camera that is mounted in a third eye view position, the camera looks at the boxes, it gets the position and the model tries to understand where to place the boxes, and the boxes are stacked. This is a stacking kind of problem which is solved here. Next, we can use RL to learn the policy for the robot, the skill policies. In this setup, we have used our RL to learn drawer opening, then opening of doors, pushing and pulling task, and picking and placing tasks. In this case, we have used MPC-based controller to learn a stir skill, where the task is to the robot would execute a stirring motion, assuming that there is some liquid or similar kind of thing in a bowl, and the robot is supposed to stir it to mix it properly. So this was learned in an MPC framework, where MPC constraint was given and the RL engine learned the task. Now, if we suppose we have learned the task, now in a situation where you have multiple objects essentially creating the clutter, and robot needs to navigate through the clutter, so that means that the robot should be able to deviate from the obstacles and it should reach the goal. So in this case, we have used SDF based approach, where we have created the SDF from the 3D data. And the left side video, you see that it's the human safe approach, where when the human hand comes into the robot's workspace, it actually ripples from its place, and when the human has moved from its position, the robot reaches the goal. Now that was the skill learning part. Now we are talking about the model where we are designing the perception stack. So in the perception stack, what we are doing is that we are trying to create a semantic segmentation model. The idea was that the model should be executable in a real-time basis, and for that what we needed a compact model. We could not go, we didn't have the luxury to have a larger parameter model, so we came up with this, where you see that the interesting thing that we observed, that when we used self-supervised learning for our encoder, it was able to capture very dense feature in a smaller network, and that actually gave the real-time performance. Here you see in the graph that the red one is our proposed version, where it was actually outperforming the SEC former model, which was a kind of benchmark in this real-time setting. And this is the segmentation result you see, and the right side top results are out of distribution results from COCO dataset. So this dataset, the right side one, was not used during the training, but it was able to perform in the out of distribution case. And the highest model, the largest model that he used, that had a 53.3 billion parameters, whereas Massformer, etc., they used almost more than 200 million parameters. Okay, so this is real-time performance with our larger model. You see, it's a cityscape dataset, where we are trying to segment the objects which are on the road, and the other stuffs are in the background. The greens are essentially the backgrounds, and this is quite a good real-time performance we have observed here. Well, so once you have developed the semantic segmentation model, we also wanted to interact it through natural language. We incorporated that the language infusion part into our model with our encoder, and we made some changes with the network, and then we have received some encouraging result. So at the bottom, you see the left side result. When we just simply prompted knife, it was not able to understand where the knife was. It was actually highlighting all the regions it thought as knife. But when you prompted, find the man with knife, a man holding a knife, you see the knife was actually highlighted. So that region was recognized by the model. Okay. Now we have the segmentation model. Now we have the grasp. Okay, right. So we have the grasping model here. In the grasping model, we have two kind of grasps. One is the shape primitive based, another one where we use diffusion models with point here. Here are the grasp generation videos. Different kind of objects. At the right side, you can see the. Okay, so these are the results from the grasp model, and this is with this shape primitive based approach, where all the objects are fitted into a particular shape, and the grasp policy was generated based on the shape. Sorry, the earlier was with pointer. This is shape based. Once we have all these tools ready with us, let us go back to the first question that we are asking at that time, that if we give a long horizon instruction to the robot, which is semantically rich, can the robot understand that? So here, we are performing certain tasks which may be applicable in a household setting. The audio is not audible here, so I'm just, basically the user is giving the robot command that to pick the yellow cup and place it in the bowl most probably. The model breaks down the entire sequence, entire task instruction into smaller segments, and that is linked with the skill repository along with the segmentation models. The robot performs the grasp. Now, here you see there are multiple objects when you have in place. Now the instruction is put the 2 bottles in the tray. Now here it sees bottles, so that means the model should understand there are multiple bottles and that should be picked up and placed into the tray. Based on the task sequence, the robot performs this task one by one. This is object transfer from the table to the human. The human asks the robot, pass me the bottle. And the right side one is the vice versa. It takes the bottle from the human hand and places it on the green plate. Now the model is able to execute the task execution, but what if one task execution fails? So what happens? I mean, is the robot is clueless about it? Let's see. So at the left side, the user is actually moving the bowl which it was about to grab. The robot understands it that the bowl was not grabbed, so it comes back again. It fails because of the point cloud, the camera was in an inclined position and it could not see the depth of the bowl inside. So the pose which was generated by the model was not very much accurate. So once it has found the correct pose, it was able to grab the bowl and placed it on the plate. So in the right side also, it failed once the bottle was moved, and it was able to place it properly in the next iteration. This is a team with which I am working with in TCS Research. They are actually implementing all this work, so thanks to them. Thank you.
Thank you, sir. Considering the time constraints, we can have the questions later during the tea break or maybe later. Now I would like to call Dr. Ravi Prakash. He is an assistant professor in the Department of Cyber Physical Systems at the Indian Institute of Science. He obtained his PhD in Control and Automation from Indian Institute of Technology, Kanpur, and subsequently held a postdoctoral position at Delft University of Technology in the Learning and Autonomous Control Group.
Should be fine. This is fine. Hello. Very good morning to all of you. Thank you so much for inviting me to this HiVe, and also I attended those foundation of the institute. It was so nice. I have been here first time, but it's really a unique IIT, and it's very, very amazing. Yeah, so I will be presenting some of the works that we are doing. So I joined IIC a couple of years ago around this, and I think even some of the topics on robot learning, what Samrat and TCS they are doing, we also were in same group before. I will present 3 very specific topics which relates to this robot learning for HRI, generalization, safety, and robustness. Little background, so I am here in CPS department. I direct this human interactive robotics. And yesterday with all this panel discussion and then the talks from stalwarts, we do agree that the future looks like human-centered. And I will talk about how this technically also translate into interaction. So there's a human, and the idea is the whole different categories of human can interact with robots, and robots has this functional autonomy in this real world, and then they can collaborate together to have some interesting things. I work on these topics: imitation learning, reinforcement learning, HRI, compliant control, manipulation navigation with applications in healthcare, e-commerce, industry, and defense and space. We have a lot of robotic systems there where we deploy this in real setups. And if we look into the details of those human interactive, how the interaction look like, I will just point here that this is the internal functional autonomy that even I think in Osama's, Professor Khatib's work, we saw how he was also pushing for the idea that we don't have to learn end to end. There should be functional autonomy, and there is a learning loop outside where you can interact and learn something which we do not know, interaction with the environment, using different kind of modalities, and there is feedback that a human can also use to actually refine its behavior. So if we go back a decade ago, there was a sci-fi movie from Disney, and they portrayed a robot. This is Baymax. He's a healthcare provider robot, and it was very fascinating to imagine this kind of robot in our surroundings. And 10 years now, at the current time, there are companies from OpenAI, this 1X Neo and Figure, which is already working on BMW, learning from data, learning from human interactions. And we can see how this AI, as we have been seeing, is disrupting and constructively also adding values to different applications now. Even the industry investment you see from Toyota, NVIDIA, OpenAI, Figure, and all of them are into this robot learning paradigm, learning from data, also using physics and so on. And we are also doing something like this, and we'll today share some of the insights that we have been doing. So this, already we discussed this very briefly. What imitation learning is actually transferring the years of expertise quickly to the robot, and then you can, the learner can very quickly learn without even having to model and so on, and that's very nicely a method which describes this. Reinforcement learning, now you improve upon yourself based on some objective functions, and while we do learn from humans like this, there is also interactive feedback which can also improve the behavior over time, and we'll see how these all 3 interplay, and with a specific focus of this generalization, safety, and so we'll assume there is this compliant control. We discussed a lot of talks. We saw how compliant is very important for safety when humans are there. So in compliant control, we have this spring modeling at the end effector. So spring, if it is the stiffness of the spring is very low, 0, then if you push the robot will just move. It will not hurt a human. It's very nice, compliant. But then if you want to stay at some position, we want to do a task, it has to be very high, and therefore stiffness can be modulated across time and space to have this safety behavior. And on top of these, now we can learn the position and the stiffness both from the human demonstration. There are different ways of collecting data: motion capture, retargeting, teleoperation. We have been seeing amazing works in, again, Stanford labs. Kinesthetic teaching, there are different pros and cons of each approach, and depending upon the task, we choose these modalities. Now we'll see how we can learn this physics-centric robot learning. So physics-centric means you learn a dynamical system, like x dot equals to f of x. As a function of state space, you know the velocity of the robot, how it will evolve over time, and you use the demonstration to this. This is a demonstration. Let's say I gave a demonstration of cleaning behavior, and then I will learn something like this, where you see the yellow color here is also the stiffness, how stiff has to be while cleaning to have it successful, while learning the flow. And if you leave anywhere, the dynamical system gives a closed loop policy to come back to the position. That's very, very interesting than conventional motion planning, where if you change anything, so you need to learn again and again. So, and the application are multifold, and we can learn it quickly. sanding application, cleaning application, and so on. So now the problem is, in machine learning, generally the data are assumed to be independent and identically distributed, which is not the case in robotics. In robotics, you teach at some point, but you want to do it in next other point, far away from where you taught, and that's what is interesting. So how do we generalize to new situation? How do we make it safe while doing this? And how do we make it robust? For example, when now the data collection pipeline can have humans which can give data, which is very, very diverse and very, very also not so accurate that we want. And then the data actually reflects in the policy, and this is gold. So therefore, we have to also make it some interesting way in which we can correct it rather than just discarding all the data that we have. So then policy generalization, we'll see how, for example, these are a stacking task. There is in factory, you always have some items to put it back on the shelf, reshelving. But then what happened, and then there's a dressing behavior. Let's say you have to do a healthcare where you want to dress, a robot wants to dress it. There's cleaning. And then the generalization would be, once I teach it only one time, I should be able to restack for all different situations, different location of the cell, different location of the start points. And now hand can change, person can change, I should be able to dress it well. Even the surface, cleaning surface will change. So I should be able to generalize across all these variations of a same task. So I just want one demo of a task, and then I should be able to do. So we came up this is a recent paper in TRO, spanning from my postdoc work, where we use deformation of the space. So idea is the previous space and the new space. For example, this green was the cleaning surface, the blue is the new surface. We find a mapping, and then we use the diffeomorphism of the whole space to then transform the policy, and that's very nice. Let's look at how it works in practice. So here, let's say you give only one demonstration of how to pick a place, an object, and then now we can change any location up, down, here, and it will use this transportation to automatically generalize. It just looks for the scan the environment to see where is the current location and the goal location, and it will automatically be able to transport the policies in real time. And this is real OOD generalization, which is very, very big point now in robot learning community with all these VLAs and so on. If you change anything, it will not work. If you change any goal position, you have to train most of the time, and it's not very easy. But this is what we use the structure of the environment and the task parameters to do it amazingly well. Robot dressing, now let's say you give a demonstration only once and one trajectory, and then you can now change the configuration, change the human hand, change the pose, it will automatically adapt. It's using the camera, and the task parameters are the whole manifold of the hand here. Before the manifold was start and goal location. And it is very generic. It applies for any number of parameters in the space. Now for contact manipulation that we saw before, this is what we saw, is a classical behavior cloning. But then now you give new surface, and it doesn't need to be trained again. Just uses camera to scan it and generalize to any different surface and the morphology of the surface, rotation, orientation, and so on. So now while we are transporting, there could be uncertainties. The object might fall off. The reshelving can be done on the real time. So we can use some automata theory or a state transition to then have this hybrid control, high-level state, high-level modes, and then the continuous motion. And then we can also use this transportation to actually do this. And there's a video here. Can you bring the mic?
Making long horizon robotic manipulation robust. First, we demonstrate a nominal reshelving task, moving an object to a shelf. When dropped mid-transport, the nominal baseline fails by targeting the initial pick location. Our method dynamically adapts to the new drop spot. Next, a wiping policy is demonstrated on a flat surface. On a sloped board with partial markings, the baseline trained on sloped board inefficiently restarts from the original location. Our method efficiently targets only the residual ink. Finally, we demonstrate a gravity invariant scooping task, transferring granular material into a bowl on the table. The plate is now kept on the shelf. During execution, a mid-task perturbation occurs. The nominal baseline fails by pouring in the original training locations. However, our proposed framework dynamically transports the geometric motion to the new pour location. Today, I will...
Yeah, so that was more about how do we use the structure and the environment task parameters to generalize. Now we can see how you can also use LLM. For example, here there's a drone which is flying, and there is let's say, surveilling an area, and we see a new intruder, and we want to actually give it a command that can you approach the person slowly and closely. So we want to adapt the drones to take a clear view of what is the intruder, who is it, is a known person. So just in natural language, let's say somebody who is in the border and he doesn't know so much of programming, right? So you can just give a natural language, can you approach person slowly and closely? So here we are doing spatio-temporal scaling on the fly, and these are multi-agentic framework of the LLMs, and then we also use optimization on top of it to make sure that this does not produce unsafe behaviors. And let's play how it also works.
Traditional trajectory planners often fail to capture user intent. Natural language offers an intuitive way to express intent. We aim to develop a system for open vocabulary corrections. Additionally, we prioritize a fully interpretable approach for natural and intuitive adjustments. Let's understand this through an example. A planner generates a trajectory for a drone to surveil a region. However, if the user needs a clearer view of an individual, they can issue a command like, "Can you approach person slowly and closely?" The system adjusts trajectories based on user preferences expressed in natural language, which on multiple robots. In this simulation, a Firefly drone was tested in PyBullet. To test its ability to follow complex commands, the drone was instructed to shift every 10 waypoints alternately left and right. In another experiment, we tested our method's ability to generate waypoints beyond adaptation. The user commanded, "Perform a 5-turn spiral with 10-centimeter radius increments at the center." This combined generation and adaptation highlights our method's versatility. Real-world task-oriented tests were conducted using a robotic arm and a ground robot. The arm collided with the red bin, so the user instructed it to move 0.2 meters upward to avoid it. Another task directed the arm to hold its position for 5 time steps. This combined task demonstrates precise corrections and multi-step execution. In another test, the system processed an instruction to find the nearest black object. The arm adjusted its trajectory and moved toward a black bag. This highlights the ability to adapt to real-time environmental context. In this loading task, the ground robot was instructed to wait near a human before proceeding to a designated drop point. The robot paused at the loading spot, waited for items, then moved 5 meters to the updated drop point.
Yeah, so that was more about generalization. We can do generalization using structure of the environment. We can use LLMs to also do it. Now we look at safety. So now let's say for a human, humans hand over a task. So a robot is giving some items to the human, and there is some obstacle now. So robot has to adapt its path around the obstacle, and then it uses policy exploration to optimize both the position and the stiffness that we discussed. And if we do so we use some reinforcement learning here, and if in reinforcement learning we directly sample, then it might lead to unstable behavior. The closed loop trajectory will become unstable. So we came up with this manifold constrained reinforcement learning, which actually will not allow the robot to even do unstable behavior, and it will be quite safe working with human. So maybe you can see the safety, how it works.
Robots in collaborative environments must adapt both motion and compliance to task demands. Achieving this requires generalizing learned behaviors to new settings while ensuring stability. CGMS addresses this by optimizing both trajectory and impedance, with guarantees on stability and actuator feasibility. Let's see how this performs in collaborative settings. Our first task imagines a simple but familiar scenario: a robot delivering food to a hungry collaborator. In the nominal case, there are no obstructions. Now we introduce an obstacle into the workspace. CGMS adapts the trajectory to avoid it, while modulating impedance to remain both compliant and safe. In the next task, the robot assists a person who's focused on their work by handing over a pen stand. Again, the nominal execution follows an obstacle-free path. With an obstruction introduced, CGMS once again adjusts the trajectory while maintaining certified stability. The impedance adapts locally, remaining compliant throughout the motion and increasing stiffness only when necessary. Now we show what happens without stability constraints. Sampling from unsafe regions causes erratic motion. The robot violates joint limits and moves unpredictably close to the human before triggering a safety lockout.
And we do it for multiple surfaces. I will just try to speed up a little bit. And the last point, we'll see robustness. So once even the demonstration not perfect, we can give teleoperative feedback to adapt on the fly. For example, this cleaning task before you saw. So let's say this is a demonstration that we gave, and now we want to clean it. We saw that it was not cleaning well, so there is a feedback that we can give from the teleoperation device, and it will automatically adapt the behavior on the fly into the learning models, and then we can also improve. Let's say sometimes we know what to do the task, but we are not able to give it well, so this interactive correction can help. And then also we have done recently that now if the data set, there is no human there, but we can automatically use some machine learning statistics to understand what is the information gained through the data set. And there are if we do just normal demonstration, the policy will learn from the bad demos. But then there are other methods in the literature that do filtering, but we do direct optimization on the data set, and this can actually solve a lot
Robotic
of
learning
problems.
often relies on demonstrations, but real-world data sets are heterogeneous. Some trajectories are informative, while others contain inconsistencies. Our goal is to better utilize this imperfect data rather than assume all demonstrations are equally reliable. We propose utility-aware imitation learning, or UAIL, demonstrated here on a pick-and-place task. Each trajectory is refined by a shared operator and a merit score, capturing informational richness, and task consistency is calculated. Then, a dataset-level global utility functional is maximized through joint gradient updates to reshape the dataset distribution. This produces robust manipulation behaviors in wiping and stirring tasks across learning methods. Unlike previous methods that discard inconsistent data, we maintain full dataset diversity and size.
Yeah, so that's it. Maybe I will skip other things. There's more details if you are interested in the works that we do. Also, maybe if the students, I have good experience working with students from IIT Mandi. And if you're interested to work with us, if you're looking for PG admissions, we have still deadline one week. You can do apply there. Thank you so much. Yeah, so I'll be available outside if you have any questions.
Thank you, sir. Now moving ahead, I would like to call Dr. Pushpak, and he is an assistant professor at the Center of Cyber Physical Systems in the Department of Aerospace Engineering at the Indian Institute of Sciences, Bangalore. He leads the Formal Control and Autonomous Systems Lab, where his research focuses on the intersection of control theory, formal methods, robotics, and machine learning. He was a recipient of the prestigious Google Indian Research Award in 2021 and has published several papers in top-tier journals and conferences. He will be speaking on safe and real-time control of robotic systems under spatio-temporal constraints.
Thank you all for inviting me for HiVe 3.0. It was interesting discussions and nice talks. I learned a lot from these sessions. Right, so I will be talking about safe and real-time control of robotic system. And I will be considering something called complex specification, where we have space, time, and logic constraints. Okay, so in my PhD and postdoc, I worked a lot with model-based control, and where we assume that mathematical model of the system is known, right? And when I started working with real robots, the biggest question is how to get mathematical model, right? The one way is like we can go for data-driven approaches or learning-based approaches to learn these mathematical models with approximations, right? But that has a big problem where if we have system which is unknown and we want to do some safety critical task, right? And where there we cannot afford error from the approximations, right? So the task will fail, right? So there are multiple aspects here. So one is like we have safety critical tasks. For example, consider this example where we have to overtake a car, right? So the failure is not option because it's very safety critical, right? And the dynamics is unknown because it's very difficult to generalize the dynamics. For example, if we have car, we don't know the road friction. Road friction keeps varies with road, right? So we cannot generalize the mathematical model, right? So mathematical model is unknown and it is not easy to derive. And we want something called real-time performance. For example, most of the learning techniques and all, they have inference time and all, right? So it is not in real time most of the times, this planning and all, right? So can we achieve real-time performance, and how we can handle complex tasks where we have space, time, and logic constraints? We will shortly see one of the example, what do I mean by those constraints. So the question here is, can we design a control framework that is safe, model-free, computationally lightweight, and formally correct, and it can do a real-time performance, right? So here is an example of high-level complex specification. Consider this drone carrying a payload, and it needs to pick up from location A, and it needs to go to location B within 30 minutes, and to deliver it, and it needs to avoid obstacles, and whenever the battery is low, it needs to go to the charging station and stay there for 2 hours, right? And you can see that complexity of the specification, we have space-related constraint. All these green keywords are related to space, obstacles, locations, and all, right? And then you have temporal constraints where you need to go somewhere in 30 minutes and just stay there for some duration. And we have logical constraints where and, or, and implication of tasks are there, right? And there is a nice field in computer science where formal languages and automata theory that can capture this kind of specification very efficiently. So we can either use something called linear temporal logic or signal temporal logic, or there is like something called automata structures that can capture these space, time, and logic constraints efficiently, right? So goal here is, can we design control algorithms that will ensure this kind of specification, and we don't want to use mathematical model, right? So here we are going to propose an approach which is approximation free using something called spatiotemporal tube. Okay, so what is spatiotemporal tube? Is basically, it is an interval which is time varying interval in a space and time, which is continuously differentiable, and so you can see that it is a space and the vertical axis is time. So we can have a tube which is evolving in time, right? And it can either be a circular tube with the center and it has some radius, and this can efficiently capture this space, time, and logic related constraints, right? Because we have time, we have space intervals, and we can also incorporate logic efficiently, right? So now the goal is, if I can ensure that if my trajectories stay inside this tube for all time, then I can ensure that my system will satisfy these complex space-time logic specifications, right? Okay, and here is the control mechanism. So if we use this control law, and you can see that this control law is basically depend on the error which is computed from the boundaries of this interval at each time, and it just compute this error, and then we have this epsilon, which is the non-linear function of this error, and if we use this control law, you can ensure that my trajectory will stay inside this tube for all time, right? So here we don't need any mathematical model. We don't need any system identification or no data collection or no learning, right? And another advantage is low complexity, is closed form solution, and you can use this controller with very less computational complexity, right? So and then you have no tuning parameters, and it is robust to the disturbance, right? So I will not go into detail in the mathematics how we can generate these tubes for different kind of specification, but I will show you very high level overview where it can be used, right? So we have several applications. So for example, we can solve this reach avoid state specification using temporal temporal aspects where we want to reach the target and specific time, right? And while avoiding these obstacles. And we can do it without knowing the mathematical model of the robot, right? We can also handle input constraints where in two ways, like if you add disturbance, it can either come back and complete the task, or it will just stop, right? So it depends on the task criticality. If it is safe to stop, if you go away from the planned path, just stop it, and then otherwise you can complete the task, right? And we can also extend it to the dynamical environment where we have environment is continuously changing, and you can see that here my tube is evolving according to the sensor measurement, and it is reacting to the environment to ensure safety. And again this is again completely model free, right? And here we show the scalability where we have hundreds of obstacles moving randomly, and we can see that we can successfully solve this reach avoid task, right? So then we extend it to some complex specification where we have specification where we start at this starting point, and then we have to keep visiting this T1 and T2 for several times, and you can see that these time intervals are there, and then you need to reach to goal while avoiding these obstacles, right? And you can see that we can generate this tube for this kind of complex specifications that will enforce that we will satisfy this specification for in approximation free way, right? And with low complexity control algorithm, right? And we also showed it in more complicated scenarios where we have multi-robot system where we need to maintain some minimal distance between two robots and switch the targets, or even like here this 7-DOF manipulator is solving a maze problem, right? So so we have these red lines which are the obstacles, and you need to navigate the pointer from the start location to end location, right? So I don't need any mathematical model, Coriolis systems or mass matrix of the robots, and it is also robust. So you can see that we added one water bottle of 1 kg. It is changing the one of the mass link to 1 kg, and still it is solving the same thing. So it's robust. It is also agnostic to the robot. I can change this robot to any other 7-DOF robot and it will still work, right? So here we are solving some complicated task where we want to exchange the blocks from different locations while avoiding obstacles, and it is also robust to the disturbances, right? And it's completely approximation free. We don't need mathematical model of the robot, right? So then we go next one more step ahead. So can we incorporate social awareness? For example, if we have these two multi-robot systems where one robot is carrying grocery and one robot is carrying like emergency, like ambulance or fire truck, right? So we come up with something called social awareness index. If it is between 0 to 1, and if it is low, it is egoistic agent, or we can have altruistic agent if it is towards 1, right? And how we can incorporate this kind of social awareness inside the autonomous control algorithms. And here is one example. So we have like two agents, one with yellow and blue. Yellow is like a more egoistic, and you can see that it is going straight, and the blue one is accommodating for the giving a passage to the emergency vehicle, right? So this next example, we just flip the situations, and then you can see that now yellow is accommodating for the collision avoidance, and blue one is prioritizing the task completion, right? Yeah, so this is very, very useful in the fully autonomous environment. We need to give some priorities to the vehicles, right? And we also showed, like, if you have multiple agents, it is also scalable, right? So here is another interesting case where it can be useful. So here there are, you might have seen these robocars, Waymo robotaxis, and they just struggle, right? In the complicated scenarios where they are not able to find solutions, right? And the main reason behind it is the algorithm sitting in each of the car has equal priority, right? So if they have equal priority, who will take back, right? So I also want to move, and both vehicles wants to move there is a conflict, right? And we showed that if we can assign this social awareness index, different social awareness index to each car algorithm, we can solve this scenario. For example, here we have algorithm with equal priority, and you can see that it just gets stuck. No one is moving. But while if you use the social awareness index, and you can resolve this kind of conflicts, right? So that is one of the application where it can be used. So the next, we also use this kind of approach for learning from demonstration, where we collected multiple demonstrations of a certain task, and we learned this spatiotemporal tube from these tasks to capture space and time related features of or intent of the human, and then we can transfer it to any robot, right? So only the robot dynamical structure should be same. Like it can be, if it is 7DoF robot, I don't care if it is of what company, right? And we can show it works all the time if we use some alteration of the robots, right? Yeah, so this is pretty much I would like to present. So we discuss a novel technique which is capturing the spatiotemporal tube that can capture the task in space, time, and logic constraints efficiently, and it allows us to design an approximation-free and low complexity control laws that can be transferred to the practical systems very efficiently, and it works. So this is one of the thread of the research direction we are doing, and other research directions, I also work on the synthesis and verification of neural networks, neural network based controllers with formal guarantees, because all these control techniques where we are using AI ML techniques needs formal guarantee, because otherwise it is of no use in physical AI systems, because they are all safety critical applications, right? The other direction I'm looking into is how we can transfer the controller designed for the mathematical system, how we can transfer it to a real system with formal guarantees, because mathematical techniques are quite rich to design controller under some assumptions, and how we can bridge this gap from sim to real or math to real. That is another research direction. And cooperative multiple robots, some of the examples you saw under constraints. Then we are also trying to define the resilience for cyber physical systems, how we can make cyber physical system more resilient, and how we can define resilience for the cyber physical systems. And the challenge here is both are talking different languages. Cyber is mainly on the discrete space, and the physical systems are in a continuous space, right? So that is a very challenging problem to solve, right? Yeah, so this to conclude my presentation, and thanks to my lab members and collaborators.
Thank you, sir. Moving ahead, I would like to call Dr. M. Felix Orlando, who is an assistant professor in the Department of Electrical Engineering at Indian Institute of Technology, Roorkee. His research spans over a wide spectrum of robotics, aerial robotics, rehabilitation robotics, visual servoing, and hand-human biomechanics. He is an illustrious alumnus of Indian Institute of Technology, Kanpur, Korea Institute of Science and Technology, and Case Western Reserve University, USA. He will be giving his talk on smart medical robotics.
Yes, thank you so much. So very good morning to one and all. Thank you so much for this opportunity. I especially thank Professor Director of IIT Mandi for this great opportunity. So I'm here to present my talk towards medical robotic systems, where I confine myself within the wearable systems, that is exoskeletons, leg and hand exoskeletons, and also towards the robotic needling systems for minimal invasive surgery. Now coming to the robotic needling systems, which are meant for minimal invasive surgery. Currently they are used with rigid needles where they do not have the flexibility, and if they have the flexibility, they are not active in nature. So this system does the brachytherapy or biopsy treatments with the help of imaging modalities as the feedback. This is the one, and there is a trade-off, as we see that in the imaging modality we have the blurriness, and if you want to have the clear image, then we need to go for CT or MRI, which does not allow you for real-time processing of the system. Then we have the second system, which I am going to discuss today quickly, is basically the exoskeleton, precisely hand exoskeleton for grasping task with the force control, and also the leg exoskeleton development and control using. That is meant for sit to stand task. Now coming to the first system, which is robotic needling system. So what we can see here is, conventionally there are rigid needles which are used in order to have the treatment for brachytherapy or for brain or for eye surgery, where the physician uses straight rigid needles in order to place the radioactive seed in the periphery of the organ of interest. Whereas our idea is to have an active, smart, flexible needle so that we can have the puncturing area lesser than the one that is in the case of rectilinear or rigid needles conventionally. So that they can conform, these smart robotic needles can conform to the shape of the organ of interest to place the radioactive seed. And also one thing that is better here is the healthy anatomical organs which are closer to the cancerous region will be ready of smart flexible needles. Now there are three main loops. The outer loop, which is where the physician is involved in order to provide you the optimal path to track and to reach the target of interest. And then we have the middle layer, which is basically the robotic system in order to have the precision or the accuracy to reach the target. And finally we have the inner control strategy for the robotic needle, because the needle is equipped with distributed sensors and actuators, precisely the high power to weight ratio based actuators called shape memory alloy actuators. So that has to be controlled, and then we have the middle layer, which is for having the precision to reach the target accurately, and then we have the physician into the loop in order to provide the optimal trajectory very instantaneously. And you can see now so this is basically the brachytherapy of a prostate cancer treatment, where you can see that a rigid needle is inserted by a physician in order to reach the target of interest. What is observed here is the prostate gland, which is in the initially it is in the shape of a ball, then deforms with the insertion of the needle, and then it comes back to the original shape, as you can see from these three photos, 1, 2, and 3. Three stages you can see. Initially the capsule is maintained, then as the needle is inserted, the deformation of the organ is visible here clearly, and then it comes back to the original shape. So what is challenging here is the target is not in the static point. It varies dynamically, not only the target and also the anatomical obstacles, precisely the blood vessels and the neighboring organs. So here is the challenge that will be resolved now. So the thing is, in the path planning, we face this challenge in to reach the target, precisely multiple targets as well as the multiple obstacles. They are dynamic in nature. So we come up with the idea of having greedy heuristic strategy based randomly exploring tree, and that also we have the reachability guided strategy, so that trajectory can be achieved by finding the start node and the random node, and between these two nodes, whether we can see that trajectory can be achieved by the geometry of the robotic mechanism, because the robotic system must have the curvature to be attained. Minimum curvature has to be attained by the passive needling system. So we have also observed that constant curvature cannot be attained in the case of real-time path planning, because the constant curvature will lead to the obstacle collision, and hence various curvature-based approach has to be attained in this case. We also tried this with single target in order to reach the single, which is dynamic in nature, and with multiple obstacles which are also dynamic in nature. We have done this with this idea of greedy heuristic strategy, and then we have also done with multiple targets. Here is the challenge here is, we have multiple targets here, and whichever target is first encountered by the needling system, we reach that. We will not go by a hierarchy to reach the targets in order. We reach whichever target comes first encountered by the needling system, and then we retract back, go to the next target, which is closer. And if the next target is in the path line, then we will not have the retraction. Retraction is a half retraction. This is the idea when I was presenting in my talk in TU Delft in 2022. And they suggested that do not have to retract completely. Have the half retraction and perform this with a one single percutaneous insertion. Try to attain it, because we were taking out and going to next target completely. So TU Delft faculty members, along with Ravi, they have suggested me in 2022, do not have to retract completely, insert it, the needle with one insertion, and then retract half so that the needle is within the organ of interest, then go back to the next target. That's how we have achieved this. And this is the experimental study that we have done with needling system inserted into the tissue. The main reason for having this tissue phantom instead of the real tissue here for the demo is the obstacles have to be captured by the vision system, because we do not have sensor to capture the obstacles within the tissue region. Whereas we have the sensor for the needling system because of this EM sensor, where we have small coil attached to the needle tip. That can be captured by the EM field generator, because this generator, this is the precise tracking system with 1 mm and 1 degree accuracy. But we could not able to capture the obstacles within the heterogeneous tissue. That's why we kept it to the best transparent, and we could able to perform this in real system. And coming to the second phase, which is exoskeleton, precisely the wearable device for assistance as well as for rehabilitation case. The first one is the hand exoskeleton meant for performing activities of daily living. So we can have two types of exoskeletons, one placed in the lateral surface of the hand, which will help you to move the finger as per the anatomy of the fingers. But this will not be helping you to provide the normal force required for performing the activities of daily living, such as grasping with high normal force. And hence we have come with the idea of grasping task, where the exoskeleton can be placed exactly on the dorsal surface so that it can apply good normal force for grasping task. And with this idea, we have moved forward for developing the kinematic model with the anatomical constraints, where we have the digital interphalangeal joint related to the proximal interphalangeal joint, and that with the metacarpophalangeal joints. And this is for the index finger. These constraints are utilized in order to derive the kinematic modeling of the system. This is precisely a closed loop system, so it is quite cumbersome to derive the kinematic model. But with thanks to these godly relationships, where we could have the simplified kinematic model in the end. And now this is the prototype that we have developed after the CAD model development, and we can see that we have external sensor, which is only the FSR force sensor, and we could reduce the under actuation. Like from the full actuation, we could come to the under actuation system for having the linear actuator for each finger. So each finger has precisely, the thumb has 5 degrees of freedom. 5 degrees of freedom is captured by only 1 degree of freedom here, and that's why this system is underactuated. And this is how we have validated the kinematic modeling kinematically, and then we moved on with the validation here, precisely obtained from the kinematic model here. So then coming to the neural network-based intelligent control of this hand exoskeleton for robust grasping task. Here, the modeling of the dynamic modeling is cumbersome, as it has the coupled way of the mechanism having the, you can see this mechanism can have the closed loop mechanism where half of the robotic system is the mechanical link and it is closed by the human link. So collectively getting the dynamic model is highly cumbersome, and hence we moved on with an idea of representing the system with models, precisely RBFN neural network models. One is the control strategy and another one is the estimator. Okay, so what happens here is, given the desired force for the next instant, we use the output of the model estimator, which receives the input from the sensors, and we could able to update the control parameters in order to get the output which is used for making this system, that is hand exoskeleton, to perform or to reach the given desired force. So what happens without this precise or accurate model of the hand exoskeleton, by using the two neural network based models, we could be able to achieve the task precisely and robustly. And this is the experiment we have done for constant grasping task. Why we go for constant instead of going for multiple step, also irregular sign trajectories of the force? First thing is, we need to grab a glass of water, and once the once the water is consumed, the weight of the bottle is, or the water bottle is reduced. So in that case, maintaining the constant force is a primitive but important task to do that. So that's why we have done with couple of trials, and we compared with our friend PID controller. And then we also did with multiple steps based approaches, so that as the water gets reduced, the weight of the water is also reduced, and hence we tried that with multiple steps with severe strict analysis. And then we come to discuss or compare that with the one that I have developed in 2020. This is the robotic system, where you can see that it is highly fully actuated direct driven system, and this is quite bulky. And the advantage of this is, this robotic system will make the finger to move towards grasping as per the anatomy of the human hand, whereas this system takes the advantage of under actuation, and it aims in not moving, rather it aims in the next level of grasping with robustness. So this is the thing. And coming to the last stage of my today's talk is about the leg exoskeleton. We have first developed this with passive system. That means with the spring and without the actuator, we could be able to achieve it. And we tried this prototype, and we have also made the system, but I didn't show that. How we do that is, basically we remove the spring, this rod is removed, and then that will help the patient to sit to stand up to the weight of 90 kg. And these are the stands that will help once the patient is sitting or the human subject is sitting. These are the two stands will help, and those two are the gas springs, which will help to lift the patient from sit to stand task. But this does not help us to stand to sit, because stand to sit is again a torture, because the gas spring is so powerful that once it is stretched, compressing by the human support alone is impossible, even with the healthy human subject. That's why we moved to the idea of active systems. That means a system that is getting operated by actuators. Could be, we have done with electric actuator, also with pneumatic actuator. And this is the system that provides stability in bidirectional aspect, where you can see that the human subject could be able to activate this system by a switch. Then it provides him the stable movement towards sit to stand, and we can observe that after completing the full standing pose, then he is pressing the switch in order to have the attained stand to sit task. Bidirectional with the stable movement is achieved. Whereas here, from the literature, latest one, you can see that The system has a linear actuator based, which is highly appreciated, but the human subject is highly doubtful and fearful, and the movement from or the motion trajectory from stand to sit or sit to stand in this case is highly unstable here. Okay, so with this I move on to the next slide of thanking my network of roboticists. So I'm afraid that I didn't miss anyone who is sitting here. So I thank my supervisors, Professor Lakshmida Bera and Professor Anupam Saxena and Professor Ashish Datta. They are the three supervisors from IIT Kanpur. I'm the only student that time with the three supervisors. And now I have my network where I have the father of modern robotics, Professor Siciliano, closely related to me because his new books he exchanged with me. And I have my postdoctoral supervisor to thank, and my inner circle, Professor Ravi and Professor Subhash, and other Professors Swagat and Professor Manavalan and Professor Ramana. I'm just sharing my third chapter in his third book. And Professor Elvira is closely related to evaluate my students' thesis. And also I thank Professor Debashish Ghosh for being an examiner for me, also for my last sixth student a week ago. Thank you, sir. And I also thank my team. This is a team which is with the 6 students graduated, and currently I have these 2 students present here. With this, I conclude my talk. Thank you so much. Yes, I'm available in the outside now, so you can have some discussions later. Thank you.
Thank you, sir, for this valuable information. Now I would like to call upon Mr. Chandan Singh, who is a senior scientist in AI and robotics at TCS Research with over 10 years of experience in robotics and intelligent systems. His work focuses on robotic manipulation and human-robot interaction with an emphasis on deploying collaborative robotic systems in real-world industrial environments. He has worked across domains such as manufacturing, logistics, and retail, developing systems that integrate multimodal perception, complaint control, and task-level reasoning. His recent research explores the realization of industrial use cases with desired levels of maturity using foundational models, including LLMs, VLMs, and vision language action models, in conjunction with robust control and efficient system architectures.
Thank you for the introduction. And I like to thank the organizers, especially Professor Bera, for inviting me for this talk and giving me an opportunity to give the perspective of industry on human-robot interface, especially for robotic manipulation in Industry 5.0 era. So I'd like to start like why this human-robot interaction has become a very central aspect for Industry 5.0. So in Industry 5.0, starting from 4.0, more 4.0 was based on automations, where focus was to remove humans from work cells and do more and more robotic automation. So unlike that, Industry 5.0, because there were so many challenges in doing that 4.0 aspects, So to bridge that Industry 5.0, decided to just build those kind of mechanism or systems to have human centricity. So basically now human should not be removed from the processes, rather the process has to be human centered. Another thing which is very important is to amplify and augment humans' ability or to work. And also one more aspect which is the industry is seeing is that from mass productions, the focus is more towards mass personalization. So previously or currently the more and more like one part fits all, this type of situation is now changing, and more and more industries targeting to provide customization for individuals. So that's the reason why human robot interaction has become very central. So when I talk with lots of customers and stakeholders, we see if we can create a good human robot interface, then we have a lot of industrial use cases which are there, which we can solve. So, and of course, like solving these use cases, the three aspects like speed, throughput, accuracy, and robustness, they are very central. So keeping these three matrices in mind, and can we create great human-robot interfaces for these use cases to solve a quite great sort of value to the business. So in today's talk, I would like to discuss some of our work which we are doing in robotic manipulation. So there are three works which I'll talk. One is our language interface for these robotic systems. So basically this is mainly a non-contact based, any interaction that we can do with the robots. Another which will be more towards contact based, the one would be handovers, like handing over something to a robot, and the robot would hand it over to something to the human. So what sort of complications are there in this, building this kind of system? And then the third one would be the physical collaboration, which is more towards these robots and human, when they are in close contact with some work or under some deeper interaction in terms of exchanging force, how these type of systems can handle that. So I'll start with the language interface for these robotic systems. So when LLM came, and at post ChatGPT moment, the robotics community got super excited, considering that now building an interface, we can directly take language and then generate actions for the robots. And lots of initial effort from Google and other labs, they targeted, and then they come up with some solutions. But when we thought like whether these solutions are sufficient to realize a use case in industry, we thought like, okay, these kind of frameworks will not work. So we have to think differently in order to achieve those reliability and what are the metrics which is being considered for industry before deploying. So we come up with a system architecture. In this system architecture, the skill library, which is the core capability, and lots of talk, which I think from my previous speaker, they kind of, it's a kind of avenue to include those works in this skill repository. So essentially all different sort of skills that we can create, like different type of perception and guided control, can be a skill part of this skill library. And the other essential component for this architecture is a user interface, basically the way through which we can interact with this system. And then the task planner that's a central component, which is basically responsible for generating plans. So the plans is essentially the sequence of those skills which the robotic system understands, or basically we can say the grounded skills which can be groundable. And the third one, which is more of a deterministic component, which is robotic controller, and it has a responsibility to orchestrate those plans reliably and efficiently. In between, if there are any errors, that it can handle those errors, but in a deterministic way. Simultaneously, all hardware controls and interfaces, software interfaces, they all need to be managed by this orchestrator. Okay. So now I'll show a demonstration. So this is what we have come up with. So assuming a robot has, for the task planning, I would like to mention, so normally if you have to write lots of prompt using off-the-shelf LLMs, it is not going to work. So we have to come up with some sort of framework where we can do planning. So we have some publication on that, on the planning aspect as well as on the overall system architecture. If you can say the command is being given and then the robot has come up with these skills. And now these skills has been performed, so each skill will have their own realization, that in terms of the perception, the control and all. So for example, if you have to create a system which can interact with a person through natural language and execute some tasks. So in order to execute those tasks, what sort of initial skill set will require? Right, for example, a robot assistant we require which can do screw driving, painting, or maybe pick and place, or different sort of pick and place. So how do we realize that? To realize, the first step would be to create those sort of skill set. So now another example we kind of demonstrated in the AI where we could demonstrate systems which we kind of worked efficiently, accurately for at least a week in the summit, that too in open. So we kind of feel like this system is quite robust in some sense, that it can handle those skills reliably and accurately, which is what industry is kind of looking at. Now I will move to the next part, which is human-robot handover. So in handover, what we observe, like there can be two possibility of handover. One where a robot hands over something to a human, and the other would be to opposite, the human hand over something to a robot. So that type of interface is also is required. So while out of these, one seems little easier, where the robot has to hand over because the recipient is a human, and human can adjust anything that needs to be done in order to complete the task. Whereas the opposite that we are demonstrating there is quite difficult. Right, so we kind of created a sort of architecture again. The specific realizations we have not covered here. We can discuss it later after this talk. So the same system, I would like to demonstrate it here. So the challenge that we kind of use the same system for one of our participation at a challenge in ICRA 2024. How to play that? I'm unable to play the video. Perceiving it dynamically is quite very difficult. And also safety is very critical because the robot has to deal with human, so it has to assess the safe picking region as well as the grasp, so that it should not make any contact with the human, and the handover should be very safe. So now I'd like to move on the third way of human-robot interaction, which is basically more force-based, where in this interaction which we have kind of created a way in which the robot and human will make force contact, and in that we have certain components which is what very relevant with what Dr. Ravi talked about, is compliance control. So the robot has now different modes of interaction. So once it needs to track the human, do the surveying, and then once it makes a contact, then either it needs to modulate its behavior through compliance-based control. So this is another work which has application in like where robot and human does a task in collaborative manner. So under the influence of force, how robots modulate its behavior, that's also very important. So now that's all with these three systems. I would like to conclude with some sort of things which we need to think, and then in order to properly realize it with the customer use cases or solutions, we need to have some sort of work which is we are still to figure it out. which is basically the safety, certifications, and understanding human and intent and behaviors. Apart from them, there are some sort of things like where human and robot will be in a same space, how to enable what sort of psychological behaviors and how do we model it with the robotic system where the humans who will work alongside the robot should feel safe and comfortable. And also we need to define balancing autonomy and human control, and of course robustness in real industrial environment. So thank you. Any questions on realizations of any of these components, I would like to feel free to reach out. And this is my email ID. If there is anything that you want to discuss or want to collaborate, feel free to write. It will be much appreciated. Also, if you are in Delhi, feel free to visit. You are always invited. Thank you.
Thank you, Mr. Chandan. Sir. So before we break for tea, we have to felicitate them. Our speakers have been. We have to felicitate them with Sol and Cap. So please come onto the stage. I want you to be here. Yes. So I will call Dr. Samrat Datta, Dr. Ravi Prakash, Dr. Puspak, Dr. Felix to be here on the dais, as well as Mr. Chandan. No, it's good. It's wonderful. He came in 2022. आए थे
So, dear friends, we are really running short of time. 10 minutes interval for the tea, and there will be a fascinating panel discussion, and then we will have another very interesting institute colloquium. So please go in 10 minutes, come back. We don't have to call you back.
Please try to follow Pauli's exclusion principle and not inverse Pauli's exclusion principle in terms of your occupancy of the seats.
Okay.
So I give it off to Professor Lakshmidhar Behera, who is going to moderate the session on. So the title of this panel discussion is Future of Human-Robot Interaction. Will the digital human emerge? So over to you, Professor Behera.
Okay. So everybody be seated. We are very happy to have a wonderful panel with me, with Professor Devashish Ghosh from IIT Bangalore. Devashish, you can raise your hand. And Dr. Amit Kumar Pandey from France. Yeah. Professor Kheder from CNRS France, Dr. Nicholas, yes, Dr. Anima Majumdar from TCS, and Ambika from France. So, as we will have, I don't think that we can have 1 hour for sure. This is 11:30, so I see maximum 30 minutes given the time is running. So, the future human-robot interaction, will the digital human emerge? So basically, let me give a background. For example, if you have a pet dog, you get emotionally connected to the pet dog. If you have left him or her in your house, you are worried whether the food has been given to him or her in right time, and she or he waits until you come to your house, and you also cry when he leaves his body. So that's the point when I say the robot emerging as a digital human. Is it possible? Of course, lot of philosophical issues are there. There are not only the robotic side where you build it, that includes mechanical design, electronics design, computer, aesthetics, its shape, its form, plus you have to bring in psychology, and can we bring in individuality? So these are some of the very, very complex topics. Professor Kheder is working on the humanoid robots. He made some startling revelation in his presentation. So the first, what I would like to ask the panel member a question that is general, and if you can give a very short and precise answer, and then we will delve into some of the intricacies of having a robot that is almost like an individual, another aspect of yourself or subject. It's not simply an object. What are the, of course, yesterday we had a similar discussion in human AI interaction. So first question to all my panel members is, if you have to keep a robot in our house, what kind of robot you would keep and why? Okay, question is clear, that if you have to keep a robot in your house, what kind of robot you would keep and why? So we start with Professor Kheder.
Thank you very much. That's a very interesting question. The time is limited, as you said, and the answer to your two questions, will the digital human emerge? The answer is yes, he already emerged, and it has several forms. There is the human as a data, there is the human as a model, and there is the human as a robot. So we already have 3 kinds of digital human. So if we have a robot that is going to, as I said in my talk yesterday, assist people, so what is the right shape it has?
No, my question is that if you want to keep a robot at your house,
at home, yes.
So what kind of robot you would prefer?
To keep it.
Keep in your house. What is the purpose? Why means what is the purpose?
Yeah, if I have to keep a robot at house, the purpose will be simply to do all the dirty things I don't want to do. First of all,
so basically an assistant you would like to
absolutely,
keep?
Yes, absolutely.
Not a companion.
Not a companion.
Okay, that's what I wanted. Okay.
I think this is a very loaded question, and it's an answer that depends on the age of the person who is answering this. If I were a child, I would like a companion who would play with me. If I were younger, I would like somebody who can talk about things that I am interested in. At my age, most probably, if there is a robot, I would like somebody who can enjoy the things that I would do, even if it doesn't really enjoy, at least express itself in a way that makes me feel companionable to the robot.
So what is that robot precisely would be?
Of course, a humanoid
As an
robot.
entertainer? As an entertainer?
As a companion. I would say.
Companion, okay. So, Dr. Pandey.
Yeah, I think since I am coming from industry, so I will have two kinds of answer. One is that obviously I will keep a robot to so that it is useful and so that more people can buy it. And then, but in terms of real uses, I think at this moment a robot which can assist in day-to-day activities and tasks that will be more critical.
So what Dr. Khatter said?
Yeah.
Same thing, right?
Yeah.
Doing all dirty things.
Like it can be, we don't do always the dirty things, but we are sometimes overloaded with many of the physical tasks at home. So it can assist in some of the physical activities, and why not also taking care of the family member, and if there is some need of immediate response when I am not at home, it can be part of that. And one of the activities which I have been also showing your work, like a robot avatar can be also very helpful, where you need a body at home, but you are not present, but you can remotely use that robot body to take care or to assist or to act in an emergency situation.
Thank you. Ambika.
Same thing. I would like to have two kinds of robot. First, the social robot who can interact with me, and if I like to listen to some songs and give me some suggestions. And another kind of robot which helped me in my daily day-to-day life. For example, living in France, you have to do the dishwasher, putting up the things. There's a lot of tasks. So I want the robot to do that for me. In the meanwhile, I can relax and gain more energy in a better way.
Thank you. Anima.
Yeah, it's a very interesting question. Mainly, it's not so far, the future is not so far that we will be having robots in our houses. So the thing is, given the choice, I like to have multiple robots in my house. So why? Because some robots will be very skillful, more accurate to do the task. Many a times, even though we are full of people around at home, but people are so busy now. With people around home also, we feel like very alone. So we need to feel like someone who can listen to us, someone who can introspect, and someone who can mirror, or someone we feel like, okay, there is somebody who can truly understand. So emotion or emotional empathy plays a very important role. So I'd like to have multiple robots rather than single robot.
Okay, thank you. Yes, Nicholas.
Thank you for this question. So, well, it's a bit difficult to come last because most of the things have been said. But according to me, I agree with Dr. Anima, that a companion would be interesting because having a robot executing cleaning task is something we already have actually. But reaching the point of having a robot that is a companion, a coach, a friend, someone who understands us, I think is the next step. And yeah, so I would like to have this kind of.
Can you speak few words in Hindi?
Yeah, sorry. So I would be interested to.
No, I'm saying, can you speak in Hindi?
Okay. तो हिंदी में बात कर सकता हूँ तो यदि धन्यवाद मैंने 2 शब्द का उच्चारण किया है दोस्तों ठीक है तो यदि मेरे घर में एक रॉबर्ट होता तो मैं एक दोस्त की तरह के रूप में चाहूँगा बस तो जो आपने कहा है मैं आपसे सम्मत हूँ
ठीक है. So I think we have achieved breaking the ice. Now let's go in details. You said, Dr. Kheder, that dirty things, right? For example, earlier time, suppose I have to write a letter to someone, right? And we dictated and somebody wrote it, right? You think a robot can exactly write in your handwriting as of the current status is concerned? We know that once you dictate, systems are already there, they hear it and convert into text, even grammatically corrected. But can they exactly imitate writing in your handwriting?
Yeah, I think the robot can do that. They can definitely write.
Are you aware of any robot that can write exactly
Yeah.
the way I write?
Yes, there
Can you-
is.
can you name?
For instance, I know I visited Shanghai and Shenzhen University, the new university. The president of the university was a former professor at Carnegie Mellon, and he loves calligraphy. He made the whole university the calligraphy himself, and he built a robot to imitate his style on calligraphy, which is extremely difficult. So I think that we can achieve with the robot the precision we want to do and AI, of course, will help to guide the motion.
Right.
But it's of course possible to have the handwriting copied by the robot, thanks of course to the AI skill. That's no doubt that it's possible.
What kind of human tasks you think robots can easily do, imitate, when you keep them as a companion in your room? And what kind of task you think they're very tough?
The task that can be done is the task where there is a motion to imitate without any decision. Okay, so writing a letter is, I need a style to copy the style, and then I need an AI that tells me which motion I have to do. But the task like cleaning under the table, cleaning the ground, that takes me a lot of time, because I have to do it like each 2 days or each day. Dishwasher, as has been said, it's extremely difficult task, okay, for the robot. Surprisingly, the tasks that are very easy for the human, because we even don't think about them, they are hard for the robot to do. And the tasks that are extremely hard sometimes for us are easy for the robot to do. Okay, there is this paradox of what is easy for the human is sometimes extremely difficult for the robot, and what is difficult for the human because it asks for precision or sometimes also dexterity, then it is much more easy for the robot to do. Okay, so
Very nice. I will take that question forward to Professor Devasys Ghosh. Devasys, do you like to cook? Have you ever cooked? You like to cook? So imagine you are cooking and a robot is there to assist you. So in the present context, where we are having a robot cooking assistant, that means when you are in your kitchen, you tell the robot to cut some vegetables or grind adrak or ginger or hand over to the spoon. There are so many possibilities are there. So where do you think that current status of robotic evolution has come that we can have a robotic cooking assistant?
Yeah, thank you, but can I just change the question a bit?
Yeah, sure.
So, when I have a humanoid robot in my house, I wouldn't like to use it for cooking. I mean, I can do that myself. I would like it to do things that I cannot do. Cooking, of course, I understand the kind of manipulative abilities, the kind of intellectual rigor you need to carry through a task is very important, but I think when we are developing a humanoid robot, let us look at what can it actually do. For example, if you look at geriatric care, I think that is very important because old people always do not have help, whereas a robot can help them. Having a humanoid robot could create a kind of empathy. That is very important for us. At my age, I still do not require this. But what I do require most probably is somebody who can intellectually match my abilities, argue with me. Of course, I already have somebody at home who argues with me all the time, but that's a different thing. I would like a robot to get into intellectual conversation with me, because that is where I think I'm using the capabilities of the human mind, which is now imparted into a robot there.
Okay. So now let us take to our industry person. Now it's a very interesting thing. So you think that we can create education robots now that would really challenge a student, okay, bring out the best from the student, okay, both in terms of logic, procedural, axiom, theorem, everything, right, in an intellectual way. You think robots are ready for such a situation? Education robot.
Yes, I think they are getting ready. They still have to evolve, but the interesting part is that we can have a robot which can let you to learn by teaching to the robot, and this is also very interesting way of learning by teaching. So we can, and robots are already evolving in the way that they interact with you in a individual manner. They try to understand where are your strength and weakness, and based on that they can even propose you some of the problem statement or answers, or they can ask you that please ask me a question on this topic. Then robot will make a mistake, then the student will try to correct the mistake, and in that way it will be engaging to achieve this kind of framework. And then we can think about higher level of concepts to be taught, including multimodality of interaction, which is very much needed mostly in the learning framework, and also the personalized learning and individualized learning. So since robotics and AI, they are coming together, and we are also bringing experts from educational background and try to understand the whole methodology of learning and teaching. Those can be created in a model which can sit within a robot, and robot is not monotonous, but it is more engaging and more dynamic, and also covering wide range of topics to teach. So things are evolving a lot in that direction.
Thank you. Ambika, you have further to add to that?
Yeah, as coming from the educational background, I think robot can be a great asset for the teachers, because in the meanwhile, for example, a weaker students need more time, like he wants the concept to be repeated. In the meanwhile, the teacher can help out and assist the children personally, and later on the children can have a good quality time with the robot, and this can bring the new kind of excitement in them to interact to a robot and learn different activities, which I feel is great, which we are developing the new features in it, so we can meet the requirements of the students as well as the teacher, and reduce the burden on them, the physical burden they put up.
Anima, when iVo came into the market, people were fascinated that it could converse with them. It's a long time. But still, 20 years back, this was a very fascinating innovation that happened. It could converse sometime, and it learned also from the companion. So now, what kind of, if you have to design iVo kind of robot, so what is that you would like to look at? That will be very interesting for you to keep at your home.
Okay. Because it's for companion robots. So when it comes to companion robots, we always want our companion to understand us. And while understanding, communication plays a very important role. When you say communication, it's not only one-sided communication, it's an effective communications. When I speak, someone listen, not just listen, it also have to respond. Say, for example, if I speak to, like suppose if I speak to my husband and my husband looking at the phone and who, saying who, something like this. So I will feel like that, okay, you're not listening. Yeah. So the person has to respond or sometimes has to summarize that what has been said, so that I feel like I'm heard. So that matters a lot. So this is one of the very important thing. Secondly, yeah, it also sometimes we expect our companion to solve certain problems, not directly, but give some solutions or some approaches so that we can look back, okay, we can say that, okay, I'm stuck into something, okay, I'm somebody to advise me. That is also sometimes very important.
Okay.
So one more thing I just wanted to add to the previous question, can I?
Yeah.
Okay, so that's a very interesting question, that's why just to add to that. Having said that, there is no bad students, there is only bad teachers. So when you say, we know, this is the era where there is lots of informations. If you say ChatGPT, it can give you information of maybe 100 intelligent human together. So we don't need just to give information to the children. In my daughter, when she was studying in class 5, she was telling she doesn't like SST. It's so boring. When she went to class 6, she loved SST. She said it's such an interesting subject. When I asked why, she said the teacher teaches so nicely. So it matters how you're connected to the student. So we need a robot which can connect, not only deliver us the information. So it matters a lot.
Making a connection.
Making a
Yes,
connection.
Nicholas, you are an expert in literature, right? And you want a robot that would converse with you almost at your equal level, right?
Yeah.
So,
yeah, yeah.
so what are challenges you feel looking at these kind of robots that I will not be able to deal with such maybe stupid robots? I need a better robots.
Okay.
What kind of challenges you, from your perspective, you think robots have not really have gone to that level where they can become equal in footing?
Okay. Thanks for this question. So, first of all, quickly, for me, the purpose of literature is not to gather knowledge, not to display all the writers I've read, etc. Is to become a better human being, right? So if I want a robot to have discussions with me on that topic, I want the robot to be sensitive enough, to be intelligent enough to point out at defect in my thought process, in my behavior, in my interactions, and maybe he could like suggest me some readings, some poems, some any part of literature that could help me improve myself. So I think this would be interesting to have this kind of, so I think maybe AI can kind of already answer this kind of thing, but having someone who, having the presence of a robot observing you somehow and being able to convey and make this kind of observation would be interesting.
Thank you. Now let us go to a little in depth about human-robot interaction. I will give an experience of mine. Recently, I wrote a book and sent to the publisher. So while writing the book, I was generating some of the images using ChatGPT and other things. So while drawing those images, I get some form that I like. Then I wanted to improve it. And I found that in such a thing, many silly mistakes these ChatGPT kind of things we were doing. And after some time, I literally lost my trust, because they only can be good at this level, but not at a level that I can send it to directly to the publications. So this trust factor for a robot to be at your home. See, repetitive task, we know what it has to be done. The contour is known. But where it's a creative, it's something that where we can interact with the robot with the confidence that whatever I want, this will be done. This trust factor. How do you see that the current level, the trust factor in terms of you as your need, you can put on the robot on a scale of 0 to 10?
So for the moment, these robots that go to the houses and do all the tasks that we have been speaking, whether it is simple tasks for us, such as cleaning, or things that any, and you see that each person basically is expecting something different from this robot. So this is also, I think the first challenge is this one. So I wanted to clean the floor because I don't like it. I wanted to wash my clothes because I don't like it. But I like cooking, but maybe just not peeling the potatoes. But he likes cooking and peeling, and he expects the robot not to do these things because he thinks that these things is good for him. Maybe he will exercise. So the first challenge is to define a robot that can fulfill all these personalized expectations, okay, of each individual. So he wants the robot to make him a better person, some others are better in whatever he excels. So you see that the expectations are high. In industrial robot, we want the robot to do this task in a repetitive way, in a very calibrated environment. And even if the environment is not calibrated, we still want the industry can define exactly what the task is to be done in this context. And the first challenge is this one. And this challenge of how to customize, okay, a single machine to the expectations of each individual is not easy to fulfill. There is no such things. But assuming that one day we will have a robot at home, the expectation and the trust will depend a lot also on many other aspects. So how many people trust, like if you put an automatic pilot or an airplane driven by the AI, so I wouldn't go into it. Okay, so I don't know why, but I would say, okay, no, but I can go maybe more easily in a car. So then it really depends on what are the expectations in terms of tasks that you expect or that you want. And then the trust, it's for me several things. It's like you have
can you give some experience, given the humanoid robots you have worked almost like 20, 25 years or 30 years?
Yeah.
Do you feel that you have achieved that trust on these humanoids to be able to deliver?
Yeah, I think it would be possible because at some point we will reach the level of technicity that would allow this humanoid to be deployed safely, because they have crossed all the security checks, and then also not in terms of hardware but also in terms of software. The fact that this robot cannot be hacked, for instance. If you have a robot, because a robot can put an action, it's not like your PC. A PC can still spy on your iPhone also, we have seen it. So, but on the humanoid robot, if it can be hacked, then it can be extremely dangerous. So obviously this mechanism has to be implemented and guaranteed. And guaranteed technically, it means. And I think it's possible after to gain trust on this robot to let them do things automatically.
So let's go to Professor Devas's ghost. This trust factor, you wanted the robot to be as your companion. How much trust factor you think you can rely on the current set of robots? If you have to get off the shelf, you have this much trust factor. Yeah. And you have less trust factor. What needs to be done to remedy those trust factors?
So I think the question of trust from a user point of view is very important, provided the robot that you are employing has much higher capabilities of functionalities. For example, if you have a Roomba robot that cleans your room, you don't really talk about trust there, not in a very big way, because trust is only limited to malfunctioning. But when you have, let us say, a companion which has an apparent intelligence and is discoursing with you, then the question of trust becomes very important there. And this is a trust that talks about whether the robot's decision capability malfunctions. So when you get into a driverless car, the first thing that would enter anybody's mind who has not done it before is that, can I trust that this is not going to get into an accident? When you have a robot companion, you should also look at what is it that you don't expect it to do. So that expectation has to be defined. Since it is a new area, we don't really have robot companions with whom we discourse in an intellectual way. Some people do it when it comes to ChatGPT, and you have seen the kind of unexpected answers that it gives. That is something that we all know. It's a matter of laughter and discussion everywhere, but it also has a very important message that robots can malfunction. They can say or do things that you do not expect them to do, that is not socially acceptable, and this is where the trust factor becomes important. And I think that is what would be interesting to know, that under what condition can I trust this. Now just one other thing, when you have a human companion, do you think that the human companion will always respond in the way that you find acceptable? No. So there is a question of distrust there. So a part of human personality also has distrust in it. So we have to accept it. Thank you.
Okay. Dr. Pandey, you say one is that the kind of assistive robots which are subservient to you, right? And there a trust factor is one kind. The other, what Professor Ghosh said, suppose an unmanned aerial vehicle or unmanned vehicle where you are giving someone the autonomy of your existence, right? These are two categories of trust, right? So can you put some, highlight both the scenarios compared to the current situation where the kind of robots that we have, where how do you find both of them in terms of comparison?
Yeah, I think because we can say that we have been among few companies in the past or people in the past who have deployed hundreds and thousands of robots in different setup with our colleague Petra, who is also sitting there. And the setups have been at home, then robots in public places, then robots who are taking care of elderly people, robots in school, and several other setups. So we have also done a study that to whom the robot should be loyal, in the sense that whose expectation the robot should fulfill. Like at home, if the robot is there and someone is saying, you are my personal robot, don't tell this to my partner. Should the robot follow that, or it should really fetch the data which it has?
Can you all be silent? Lot of noise is coming. Yes.
It is working. So that is another way of following, and they are trusting you that there is a noise. So this is the kind of thing, like the robot should follow whose advice, and who should expect that this robot will follow my advice? This is a question which is still unanswered, because if you will ask this to a community, you will get diverse responses. If you will ask this to an engineer who is designing the robot or programming the robot, you will find a different kind of answer. So there is no universal rule book to define the trust, define the loyalty about trust and honesty, and what should be the priority. So this is something which we have to define all together, and as you rightly mentioned, that in different kind of scenario, even the definition can change, the priority of robot can change, and their decision making can change, and this should be collectively defined. Intelligence is evolving, but the boundary that how they should be behaving in a trustworthy manner, from which perspective, it is still ongoing work.
Ambika, given a manned aircraft and unmanned aircraft, Which one would you choose? Manned aircraft, unmanned aircraft. Which one would you choose?
I would right now go with the man, not with the autonomous. It depends. Yeah, because it depends on the trust. Like if I have been traveled before, so I would like to go for that as well. But right now I'll go with the man, not with. I cannot take risk right now.
But if you get down in Singapore airport,
yeah,
you only have unmanned cars.
Yeah. But I'd really like to try the technology, the new technology that is coming up and the new thing to learn, because I really want to try it. But if I've given an option, then I would like to go right now.
Okay. Yeah,
Sure.
yeah.
It depends who is the man behind. So yeah. But I simply wanted to add one very important thing, because we put robot in home for a healthcare setup, and sometimes we have seen that people are even asking robot to look back because they are going to toilet or changing clothes or doing something which they don't want to be captured even by the robots or even by the sensor. So this kind of thought process, which gives us a different kind of definition, that if robot is autonomous, intelligent enough, or it is sharing some kind of information or data, or if there is someone behind the robot which is controlling the robot. So and this changes. So that's why your question was very relevant, that if it is manned or unmanned and who will have.
For example, I have the buddy robot at my home. If I'm doing some activity which I don't want, I try to switch it off so that the camera doesn't capture me. Because I don't know, maybe the company who has made it is taking all my information. At that point of time, I make sure it's switched off so that my personal information don't go away.
All right. Anima, how do you see your privacy in the front of your robot companion?
Yes, that's a very interesting question, because privacy plays a very important role. Especially when it comes to this growing AI, privacy is very crucial. So when I will have a robot, and that too not only for daily task or some automatic task. When I will prefer to have a robot which will be my companion, privacy plays the utmost importance. So in this case, I will prefer to have maybe temporary storage rather than storing the data in the cloud. It's very important. That's why maybe with these robots that we are going to develop, we should have, instead of directly connected with VLM or VLA or LLMs, we should have our smaller architectures, which will give more importance to the privacy. Because it's not only for adults, it's also for children. For every phases of human life, privacy is very important. Anybody can harm.
So what you are thinking about, what steps must be taken that privacy can be a part of designing this kind of robots?
Yes, this is again very interesting question, because we are thinking that ChatGPT has come, LLM has come, VLM has come, everything is solved. No, it's not solved. Why? When you say, hello? Yeah. So it's mainly data driven. Lots of data is given. So it has been trained, and it is working relatively okay for general populations. But we need personalized solutions. When we want a companion robot we want who will understand me. Suppose when I said something, I said a story, suppose for an elderly person said something to a robot should remember, okay, last day you have discussed about that friend. The robot will ask, okay, how is your friend now? So robot has to evolve. So while the robot will evolve, it will store the data. Obviously, it will store the data temporarily, and evolving also has to be in a real time. At the same time, robot should mimic. Yeah, that is a part of it. So there are many parts of it. One of the part is, while the robot will evolve, memory plays a very important role. When you say memories, in human mind, if you see, there is working memory, there is say, episodic memory, so different layers of memories are there. Some informations which are not readily or daily use that gets eventually stored in subconscious mind, or maybe long-term not use goes into unconscious or preconscious mind. So eventually our, as of now, those existing AI models dumps all the data into one place. There is no categorizations. So we should, there is now time is there, we should think more about the brain, more about the memory storage, how it works.
Okay, Nicholas, on the same question, would you?
Okay, so I agree with some parts of what has been said before. First, coming back on the expectation, like the robots you will have at home, like I think when you're a company and you're selling a robot, you have to communicate clearly what it can do and what it cannot do, because as consumers, I think the expectations are going to be very high, and if you don't want to disappoint the buyers, the people, the consumers, I think this is an important point, first of all. What else can I say? When it comes to storage and memory, well, I mean, there are some, how to say, dilemmas and challenges about this that we are already facing with AI. For example, if we don't want the robots to remember, to have a temporary memory, then maybe we could set it ourselves, like how long they can remember, 1 year or more. And but the risk is that we could not use the whole potential of the robots and of the intelligence because it's going to be limited by our own settings.
Yeah. So thank you. So because now the time for Institute Colloquium has come, I will end with a question that I may ask few of you. For example, Professor Osama Khatib was talking that we are able to now transfer the touch and feel. You think that robots can feel? Suppose in normal exchange, when we talk about companion, we talk about that we first hug each other, right? So in that hug, there is a warmth. We feel we are friends. You think that robots have come to this kind of status that the robot and a human can hug each other and feel equal joy?
This is a very deep question. The answer is simply that one day I was asking many people and my colleagues, I was forbidden my students to put intelligence in the papers unless they define it to me clearly what it means, at least for us. And I was talking with a very high standard scholar, which is very known in France. I asked him, okay, can you define what is intelligence? Before putting it on a robot, tell me what does it makes us intelligent? He said, you know, there is as many definitions as you ask people for this. That's fine. Define it the way you like, and then you implement it the way you have defined it. So feeling is the same thing. If you define it as just a sensor that transmits data to your brain, and that from this data you process emotions or thoughts or whatsoever, this is the definition you put on it, then implement it this way, and then in this way, yes, the robot can feel, because we can embed the robot with sensor, we can then put the behavior we want on these sensors, and then the robot will act accordingly. If this is your definition of feeling, then yes, it is implementable. But your talk, you have defined something which is more deep. I would have done my talk differently if I knew what you were doing before. Consciousness. So if you say to the people, can we implement consciousness on the robot? Then I will tell you, okay, define it to me in a way I can translate it in math, and then maybe I will try to put it. But then you will tell me your definition is not good, because I see it this way. And maybe it's the same thing for intelligence. If you ask what's consciousness, which is a very deep, philosophical, like abstract things that everybody is saying, but nobody can define it like very precisely. And it's just fine. Then we can maybe implement consciousness at the condition that you tell me what it is.
Very nice. Dr. Ghosh.
Human beings feel, but robots can pretend to feel. The biochemical processes that is behind our feelings or emotions are still, I think, far beyond that of the robots. I do not know if it will ever happen. But just to keep it short, I would say that I hope that the robots can pretend to feel and the human beings can accept it. But I hope that this exchange does not stop human beings from feeling and being emotional.
Okay. So, given the time, I would stop here with few comments. You see, when we talk about human-robot interaction, we are always interacting in terms of manipulation, locomotion, and varieties of ways where robot follows precise behavior. But as a human, we are highly unpredictable. Our behavior is not always the same. Our persona always changes. And to recognize those things, we have to go back what Dr. Kader said, that we don't understand even our own self, our own predictability. We don't understand. And one of the good part of human existence is that the unpredictability about us, it makes really very interesting. But beyond that, the sense of I-ness or individuality is, we don't understand even. So there are two things. One is artificial intelligence and there is natural intelligence. And robot as of now operate on AI, and they don't, because we have not understood what is natural intelligence. I don't think robots ever will be able to come on the foundation of natural intelligence. So with that, it is very interesting to let you know why I started doing research in robotics and AI, because I wanted to know myself better. And if such discussion, such exploration, such research helps me to enter within myself and understand myself better, I think the job is well done. We don't have time to proceed, also taking questions from you. I allow SRC to close the session.
In fact, this is an unending discussion whether robots will ever be human beings, and we only had a short 40-minute session. In fact, such a kind of discussion should last for much longer, and it's an endless debate. And I also leave it open to the audience to take forward this question to their home and think and gloss over it, whether it's ever possible to create an artificial human being with artificial nervous system and everything artificial. So let me do the final onus. I request AVM Sinaji to kindly come up to the dais and honor the delegates, the panelists and the moderator. Please give a huge round of applause to the panelists for the enlightening discussion.
Okay, please come.
So before the thing arrived, what I gathered from Dr. Nicholas and Madam Anima, whatever you wanted in the companion is the minus what you have. Means if you have somebody like she said, ki my husband, if I keep reading and if he say yeah, I want somebody who criticizes. And Dr. Nicholas said, if I have, he's a literary figure, he wants somebody to criticize him. He wants a critic. not who sit clapping. That means whatever you have, you want something opposite. That is the beauty of the nature, what Dr. Behra said.
Bring. उधर देख दो.
Sir, you have to understand yourself. पहले आप
Yeah.
Moderator has to be stuck.
नहीं, अरे मुझे नहीं चाहिए. हाँ दो. हाँ.
Next we'll honor Anima.
नहीं, अभी दे देते हैं. हाँ, तुरंत. Yeah.
We shall honor Ambika Chopra next.
Quickly.
Yes. इसको बंद कीजिए और चेक कीजिए वो चल रहा है.
Sir, with the age, the companion changes.
Different age has different requirements.
You went into philosophical mode.
So we will have a group photo. Please. Please.
तो अलग टोपी हो जाएगा. अब सही है.
Thank you, everyone. While we were all attending these rigorous sessions, there were some parallel activities going on. There were two poster presentations. One was on theme human-robot interaction, and there was another poster presentation on thematic area, multimodal AI, was going on. So, and there was also a startup grand challenge, which was organized by Technology Innovation Hub IIT Mandi on the theme of multimodal AI. I have the list of winners in my hand. I will, in the interest of time, I will quickly announce the winners. And I would like to call on stage the jury members also who helped us in evaluating these poster presentation. Dr. Sanjeev Nara, Dr. Anshu Bamne, Dr. Praful Hambarde, and Professor Shubhajit Roy Chaudhary kindly come on stage for the handing over the awards to the winners. This was the jury for multimodal AI poster presentation. I also request Professor Partha Pratham Chakrabarti to kindly grace the stage and hand over the awards to our winners. The first prize for the multimodal AI poster presentation goes to Professor Pawan Goyal from Indian Institute of Technology, Kharagpur. The poster title was Large. Can we have the winners on stage, please?
So I have to come 2,000 miles to give you a prize? No, 1st of April में करना चाहिए
The second prize for the poster title goes to Mr. Anand Kumar, PhD scholar from IIT Roorkee. The title of the poster was Touchless HCi for Media Control Using Hand Gestures on NVIDIA Jetson Nano. May I have the winner on stage, please? The third prize for the poster presentation goes to Ms. Ankita Saxena from lovely Professional University, Jalandhar. The poster title was Alveo Multimodal AI for Lung Cancer Risk Stratification. Ms. Ankita Saxena, please come on stage. Can we make it quick?
Congratulations.
Come this way.
Yes.
Hold it, your prize.
May I request Professor Bera and Professor Chakrabarti to quickly felicitate our jury members. It will hardly take a minute, sir. Thank you. Professor Shubhajit Roy Chaudhary. Quickly. Dr. Sanjeev Nara. Dr. Anshu Bamne. And Dr. Praful Hambarde. I also have the results of the Grand Challenge winners with me. We have top 4 innovative startups in multimodal AI. We had a tough time in selecting them. I would like to call upon our startups on stage. MedTrain AI Technologies founders, Mr. Nilabra Banerjee, Mr. Shatadru Ghosh. Sham Innovation founders. Sham Innovation founders Prateek Raghuvanshi and Akhilesh Raibhog. Rubric Systems founders Mr. Suresha Ramchandra and Ms. Shamshita Anand. RoboSurf 4 AI founder Mr. Praful. The first prize is being shared by 2 startups, MedTrain AI and Sham Innovation. Yes.
All insider trading, sir.
And the second prize is also being shared by 2 startups, Rubric Systems and RoboSurf 4 AI. Can we have the founders on stage, please? Over to you, Dr. Jagdish Kani. Thank you, sir.
Good afternoon. In continuation to these prizes, we also have a poster presentation for HRA track. We received around 50 posters, and we had 9 jury members: Dr. Ranjit Nair, NIT Calicut; Dr. Samrat Datta, TCS Research; Dr. Anima Mazumdar, TCS Research; Dr. Kaushik Haldar, IIT Mandi; Dr. Radhesham Sharma, IIT Mandi; Dr. Ambika Chopra, Shakti Nova, France; Dr. Nicholas Boyne, Principato, in Alco; Dr. Mr. Siddharth Sood, AA Botics, Chandigarh; Dr. Deepak Rena, IIT Mandi. And out of this,
Don't call them.
We are not. Yes. So out of these 50 posters, we have actually selected 3 posters for the prizes. The first prize goes to IISc Bangalore for the poster title Diffusion Pack Bin Packing with Custom Human Preferences by Anurag Maurya, Shivam Vats, Gautam Balachandran, and Raut Prakash. Yes, please.
Please bring it.
The second prize goes to IIT Mandi for the project poster Autonomous Wheelchair Navigation in Cluttered Environment by Siddharth Tiwari, Madhukar Vaibhav, Dr. Amit Shukla, and Professor Lakshmidhar Behra. And the third prize goes to IIT Mandi for the poster titled HRI Simulation of Vision Guided UVMS under Hydrodynamic Effects for Subsea Intervention Tasks. The prize winners are Harsh Yadav, Bhushan Tool, Kishore Kumar Das, Rishabh.
Congratulations.
Kishore Kumar Das, Rishabh Singh, Jagdish Kadiyam, and Shantakumar Mohan. And we also had sort of a commending responses from other posters also. I'll just read their names because the scores were very close. So we had the fourth sort of a prize for Mrityunjay Haldar and Ravi Prakash from IISc Bangalore, Sanjeev Anigol and Ashwin Deshmukh from Samsung Innovation and Labs Private Limited, Mr. Umar Farooq and Jagdish Karim from IIT Mandi, Saumyadeepta Nath, Pranav Tiwari, Prasanna Kukde and Ravi Prakash from IISc Bangalore, Dharmendra Sharma, Achit Sharma, John Rabiro from IIT Mandi, Prabhat Thakur, Rithilesh and team IIT Mandi, Team Dimos, Mars rover from IIT Mandi. Thank you.
Introduce you and I will have to speak from here only, no? Or is there a slide changer? No, from here. Take it. Slide changer. Slide change only slides. He will help you. Slide changer? Huh? Or the column mic hai ya?
Okay, so I'd like to welcome all of you to this Institute Colloquium talk. It's my honor and pleasure to introduce Professor Partha Pratham Chakrabarti. Sir has completed his BTech and PhD from Department of Computer Science and Engineering from IIT Kharagpur, 1985 and 88. And then he joined IIT Kharagpur in 1988 as a professor, a senior professor. He was working there and he joined IIT Kharagpur as a professor. Later, he became the director of IIT Kharagpur in 2013 to 2019. He was also having additional charges of director IIT Patna and IIT Kalyani. His area of interest, he has worked in so many different areas, AI, algorithms, formal methods, CAD, VLSI, embedded systems, fault tolerance. He published more than 300 papers and supervised more than 30 PhD students. He worked very closely to several government agencies and have completed more than several hundred crores of projects, including collaboration with MHRD, DST, CSIR, MITI, INSA, Volkswagen, Intel, Synopsys, so many things, Google as well. He started initiation of so many different types of national academic, national initiatives such as National Digital Library, Spark, Imprint, GAN, PAN IIT ONGC, and so on. He has received many awards, President of India Gold Medal Award in 1985, then INSA Young Scientist Award, Bose Award, Young Engineer Award, Shanti Swarup Bhatnagar, as well as he was the J.C. Bose Fellowship as well. And he's being elected as a Fellow of Indian National Science Academy, New Delhi, as well as Indian Academy of Science, Bangalore, Indian National Academy of Engineering, and the West Bengal Academy. So with this, now we have a full hall. And just to say that all the students who are interested in AI, ML, machine learning, they are doing our courses over here. Sir is a pioneer in this area, and second year, third year, final year, I assume all of you are being here. Feel free to, interact after the talk, and I hope that you are going to enjoy the talk. Thank you very much, sir.
Thank you. Audible? Can check. Hello? Am I audible? So good afternoon, everybody. At the outset, I am grateful to Professor Behra, IIT Mandi, and every one of you for having come here to listen to a talk which may turn out to be an April 1st talk in some form. So on the left, you see the Concorde aircraft, which had a panel of more than 1,000 switches to be controlled by 1 or 2 human beings. That is what human beings were capable of doing when we flew non-autonomous. As we have tried to attain autonomy, and we have seen all this throughout the day, 3 days, we have also tried to humanize AI. And the end result of humanizing AI in China ended up with the robots conferring among themselves and going on hunger strike because they were given more than 8 hours a day of work. So life has become very complex. All knowledge, which is the main pursuit of institutions like ours, grows in a few steps. The first step of knowledge is observation. And that is what happens in AI itself. You start observing. And it is through observing that you gain new knowledge. Whether it is discovery of fire, whether it is finding out electricity, or whether it is finding out the mood of your girlfriend, everything is based on observation. From observation comes theory. That is when people develop Newton's laws of motion, or theory of relativity, or chemistry, or molecular formats and things like that. And in AI, we end up developing models. After that, knowledge expands into applications. And from applications, it moves to economy of scale. The mobile phone that we have is knowledge at your hand at economy of scale. You walk around, unless they are very, very below the poverty line, everybody has a phone of some sort or the other. Throughout this, incremental improvements are the constant of all innovation. When we were young, a fountain pen or a wristwatch was a prize. Today it is available even in an ordinary shop. As knowledge grew, human beings realized that for every individual human being or a group, it is not possible to own and gather and know everything. So human beings created the first mistake or good thing, whichever way we talk about it, is that they started dividing knowledge. So knowledge started getting divided into mathematics, physics, chemistry, biophysics, chemical biophysics, mathematical chemical biophysics, and we started specializing to know every special topic very, very well. But in order to try and get people to know only very small topics very deeply, we started losing track of the connection between topics. And as we started losing track of connection between topics, knowledge systems, scientific systems, economic systems stopped talking to each other. And because they stopped talking to each other, this division of knowledge has created some of the biggest problems that human beings have ever done. That is when we try to optimize something, we do not check its effect in the environment. Therefore, the planet has suffered, people have suffered, there is poverty, there is digital divide, there is enough food in the world, yet there is hunger. All this is because we have divided knowledge. The first step at integrating knowledge came from the concept of computing. Computing became a general purpose method, and this general purpose method was able to model any discipline. Therefore, all of us know we have computational physics, computational chemistry, computational biology, computational linguistics, computational social science, any subject you talk about, the power and universality of computing ensured that computation started integrating every discipline. Computation therefore became the spouse of every discipline. But still, the spouse of physics was not talking to the spouse of chemistry. It is then when AI came into being, and AI evolved from the time computing evolved. And AI started integrating across disciplines. And this is what I will try to share with you today. So from computing to artificial intelligence, the core problem of artificial intelligence is the core problem of automation that humanity has started developing, whether it is the wheel, or whether it is the steam engine, or whether it is the industrial revolution, or anything else. The power of automating everything. Now this everything, which means that instead of writing a separate program for Google Maps, or chess playing, or robot assembly, or chip design, or timetable scheduling, or solving a math problem, we wanted to find a single unified solution. A single unified solution says that I will give you a statement, which is the problem statement. I don't care which discipline it belongs to. And you will have to use all the knowledge that is available to solve that problem. So which means that we wanted to automate everything. Now this automating everything hits also something and has started hitting something that is very valuable to us, which is automation of thinking, automation of creativity. So let us now look at what was the difficulty. All of our sciences ended up first trying to find closed form equations of things or models of things which human beings can understand. Slowly we converted it to, but functionality of complex systems, including nature, cannot be modeled by equations, closed forms, and the connectivity between things. So human beings, the AI people, over years, developed what I call the star of AI. So in order to be able to solve any problem of any domain and across domains, I need to have a representation. A representation that can represent, quote unquote, any problem. The second format below in this upper triangle is that given a problem in any representation, I need to have a general purpose solver which will solve that problem in any representation. And the problem that I want could be that write a poetry in the style of Wordsworth which will explain theory of relativity. And you try it on ChatGPT, you will get the answer. And everybody will get a different answer. Very interesting. The third leg, which was new in the formulation of AI, was that whenever I solve a problem again and again and again and again, I solve it better and better and better and better. How do I do that? After having solved the problem, I I am able to improve my representation and I'm able to improve my solver. So this added leg, or the third part of AI, is called learning. If you unveil AI, you will end up with this upper triangle. It has got representation, it has got a solution methodology, and it has got a learning methodology. And each reinforces the other. Better learning improves representation and solver, better solving improves learning and representation, and better representation improves this. AI people have a peculiar trait. They find out what other people have done, make improvements over it, rename it, and call it AI. The first is all of algorithmic methods of representation, general purpose solutions, and general purpose learning algorithms were integrated into AI, so they are all step-by-step methods. They are all step-by-step methods. All the algorithms, if I have to go from here to there, what will I do? If I have to play chess, what will I do, etc., etc. So, representation like data structuring or state spaces, solving meta-algorithms, meta-heuristics, and learning was renamed symbolic AI. Some new additions were there, but AI people have the habit of stealing other people's things and renaming it. Then we found that a large amount of problems comes only from data. So other than the problem itself, data, if I want to find out where is the thief, where the next robbery will happen, whether something else will happen, that or the weather I have to predict, you will notice that just an algorithm, a crisp algorithm, does not work because you do not have all the information. The system itself is probabilistic, and therefore statistical methods have to come. So the second part of AI, the second dimension of this lower triangle of AI, was statistical. So AI people took everything in statistics, from representation to statistical inferencing to statistical learning methods, added new things and called it data science. As I told you, they changed all the names and rename it and call it, made it part of AI. The third leg was the most interesting thing. Even with all these things, people were unable to solve the following problem. If I give any one of you a photograph of Professor Behra, you will instantaneously recognize it. In 1 minute, you will know it is Professor Behra. Even if you hear his voice, you will know it is Professor Behra. But the problem is, whereas in the other two cases, if I tell you how do I go from here to Chandigarh, you will tell me the steps. And if I tell you how did you come through it, you will know how I have got through these steps. But if I ask you, tell me, prove to me that this is Professor Behra, will you be able, anybody who will be able to prove that this is Professor Behra if I give you a photograph? You will not. You will write hundreds of pages. Eyes are like this, ear is like this. No convincing proof. The only proof that you will give me is, it looks like other photographs of Professor Behra. So this is this third leg of what is called cognition. Whereas procedural and statistical AI, they take time to come to their conclusion, but they can explain their steps. Whereas cognition is instantaneous. In fact, I assure you that if I give you a picture of a 5-year-old Professor Behra, I have not seen that picture, 80% people will recognize him. But you cannot explain. You cannot give a convincing explanation. Like you cannot explain why your wife gets angry, right? So none of us can explain. We have stopped trying to explain also. So combining these three, the model that people came out with in order to solve this cognition problem is the use of neural networks. It is still a model. So today's modern AI has a combination of symbolic, statistical, and connectionist models which can do representation, reasoning, and learning. And this combination does all of it together, and that is what you see in this huge, powerful AI that we are looking at. And that already, as we all know, is creating the magic of being able to write poetry, being able to do so many other things. The one more model that is coming up, which is bottom left here, and which is going to change everything and steal all your money from your bank and everything else, is when quantum comes, all your encryption will go away, everything will go away. So a new form of life will come, and more methods, human being devices, AI will be able to integrate into this triangle. All of AI is foundationally search. I am exploring a solution. I am exploring a solution. So all of it is a systematic exploration of a space of possible solutions. That's all AI does with all its methods. It also uses logic, it also uses natural language and other things. And there are several other things of AI which I won't come to. These are glimpses of AI's past conquests. Can anybody tell me which is this top right guy? Hand on his face like this. Anybody? This is Garry Kasparov when he first lost to a computer. Today, the best human chess player, if you rate computers and human beings, the best human chess player is ranked below 100. More than 100 is their rank. More than 100 automated chess players are better. There was this famous Turing test, which says that if I cannot make out on the other side, whether it's a human being or a non-human being, then we have attained AI. But we have attained even that to some extent. Then the robo-citizen. Today, when an aircraft flies, a Boeing aircraft flies, the complete digital twin of that aircraft is simulated constantly. And if there is a problem, then from here they try to locate and solve the problem. And if, I think some of you have a lot of discussions.
Can you all leave those who are shouting? I dare to say you please leave this place. I think Aditya brought the wrong people here. They are not fit for IIT Mandi studentship. Sorry, sir.
No, it's all right. So this aircraft, when it lands, either it has repaired it on the fly or a replacement is ready. If you have seen, it takes 4 minutes for any information to go to Mars. And this small Mars rover was roaming around. And we were just talking the other day that digital surgery has become so sophisticated that it is much, much better than human beings. But, now comes this new magic called Mahatma ChatGPT. Any student you ask, मैं ChatGPT से पूछ लेता हूँ. So, if anybody asks, in a single slide, in a single method, can you explain how this works. So let us go back to our model of representation, solver, and learning. So there are two components. The component on the top is called the predictive model. What it does is, it has encoded knowledge, whether it's a picture or a sound or color or voice, and it is able to train itself by this triangular method of all these methods that we spoke about, to start saying that this picture looks like a male, this person is in walking posture, this person is about 60 years old, and so on and so forth. What it does for that is, it creates this orange bar. This orange bar is the representation. Now, what is this representation? In order to give you a very simplistic view of this representation, all of us have done XY plots in science, which means that given X, given some data, given X, I've got data for Y. Temperature versus expansion, and so on and so forth. So I have got up some pieces of data, and for an unknown piece of X, I want to ask, what is Y? And for that, I create a so-called model. This model, this X by Y, is the data that I have. And for that, I create a compact model, which could be an equation or anything else. Now assume that this one dimension is having 1 billion dimensions. It is data, it is picture, it is voice, it is everything that you have collected. Trees, leaves, all of these are my x-axis, and y-axis is color, branch, voice, etc., etc. So this is this representation, which in a loose sense is a representation of a 1 billion by 1 billion regression matrix in a compact form, so that when I'm given X, I predict Y. The reverse, so this is also, this representation formation is also called encoding. And this encoding is there in the 3 dimensions that I talked about, and the 4th or the quantum dimension will also come. I'm not going to nitty-gritty details. The second part is interesting. Now, given the representation and given a small query saying I need the picture of a man walking 60-year-old, then it will use, now you are given Y and you are asked to produce X. Given Y, you are asked to produce X. So any of the 100 billion Y dimension point, and you are asked to predict a good X dimension unknown Y point. So that will now use the representation and the query and decode this and produce the longer version. It will produce a picture, a song, a video, a poem, a speech, or whatever. This is called decoding. While this is called predictive AI, the right-hand side is called generative AI. It is generating a solution. So in one shot, with the representation which is obtained by learning, training, and several other things, you are able to encode the model and decode the model, and therefore you are now able to create new items, so-called new items, which are a point on that billion 100 billion by 100 billion space. It is just a mathematical point converted into this. And in the generative part, given the model, when you give the input, what is the input? What do we call the input now, nowadays? We call it a prompt. All it does is it converts that input into this representation and computes a projection of that representation. Once it computes a projection of that representation, it gets that projected point and converts it out into whatever you need. Now that it is just a regression problem in that loose sense, what is, when you are looking for an unknown point in a regression problem, you get an answer. What do you think happens to that answer? What is one aspect of that answer it contains? What does it contain? It contains regression error. You get a point just next to it. Instead of that exact point, you get an approximate point close to it. So now you have asked for an English sentence in some form, and you get something close to it which will contain errors. To us, it's a mistake. It is just a regression error mathematically. Being a regression error mathematically, as I said, we AI people don't want to tell people these are all normal, simple things. We call it what? What do we call it nowadays? We have given a nice mouthful name for it. We call it hallucination. It is nothing, it is a regression error. The more you reduce this regression error, the better and better it becomes. Obviously, it is not the same regression problem we studied in first year or in 11-12. It's a much more sophisticated technology which is solving so many problems, and I will come to it. But this is all that is there to modern AI, the large language models. And then the next step, if you are rich enough, you can collect all knowledge in the world. And because you can collect all knowledge in the world and encode it in that representation, you create what is called the foundation model. It contains everything that is available. And then you have this foundation model and you want it to work on tea leaves of Assam. So you then do what is called fine-tuning. You reduce that model only to cater it to that tea leaves of Assam. And then people said that I will now reduce that querying and fine-tuning to just English language. Actually, this English language is also converted into a representation and mapped. But because we want human beings to interact and pay for it, we use language. But language is an approximation. Then comes the most difficult part, that AI was not yet a human being, is not yet a human being. Therefore, AI did not know what is abusive, what is obscene, what is bad, what is good. And if you start producing all that as outcomes, not only will the outcomes create chaos for humanity, but those who produce these outcomes will have court cases against them. So to sanitize this, people started developing models which are trying to make it human-like. And this was the pre-training plus RLHF, reinforced learning with human feedback. And this has come at a price. The price is as follows. People in very poor countries were paid a pittance to look at obscene, horrific pictures, photos, sentences, and label them. This is bad, this is good, this is bad, this is okay, this is bad, this is okay. Because the amount of money they were getting, maybe $1 a day or $2 a day or something like that, was more than their weekly income. But at the end of this 1, 2, 3 months of work, they were psychologically shattered. Because they have been watching certain things that human beings don't even watch 1% in their whole lifetime. They have watched. So it has come at a cost of humanity that we are not seeing obscene things. Our children are using safely and things like that. Has come at a big cost. Then comes this new dimension. This new dimension moves from a natural language input. Now, as we were just talking a little while ago, it's like a companion. You are discussing with AI. Can you do this? But this is not right. So can you find another way out? Etc., etc. So this is how, you start using these agents. And I'll tell you how students use agents so nicely. So we have a professor, students, as usual, the semester viva is on 10th, and then on 9th or 8th or 7th, they will come for permission to give the presentation. They have not appeared in the whole semester. Sir, please give me some time, I want to meet you. And then there are some professors who will say, no, you have not come, I will not meet you, I will not allow you. So what do the students do? Please sir. After some time, one of our students said, so after 3-4 interactions, he wrote a nice prompt to ChatGPT. This is my professor. We all know how tough he is. This is the past interaction. Now please write a nice email on my behalf in such a manner that he will allow me to meet him. And he succeeded. So today's AI has moved beyond LLMs into agents or solvers, individual solvers. A physics teacher, a maths teacher, a math solver, a chemistry equation solver, which can do specific tasks. And by combining them, they create, not only, they just don't give you the answer, they give you the plan for solving the problem. They give you a plan for solving the problem. And based on this plan, this new architecture has now moved on to become goal-driven, self-evaluating, adaptive, and collaborative. So you have a number of these small AI tools which are working with each other to solve a problem, interacting with each other, learning from each other, and things like that. And as we are going and moving ahead, you have seen that LLMs are now moving on to become large AI agents. And these AI agents are now becoming agentic systems. So the whole companies, their platforms, and every other thing. And eventually we are going to have a complete agentic infrastructure in place, which will replace all our ChatGPT, etc., etc., etc. The next is the more interesting and critical part, where AI is sensing data. Somebody is sensing it from outside is one thing. But once these sensors enter us, they are going to start measuring our heartbeat. We had a little bit of discussion about, Professor was mentioning, it pretends to understand emotion, which means that it will now collect all your heartbeat, your sense beat, and things like that. And the joke I always crack is that after some time, you will tap to your computer or your AI, and say, "Arey, mera to urine problem ho raha hai, I'm having urine problem." So, say, "Okay, wait. After 15 minutes, is it okay now?" Now it is okay. What did you do? "Arey, you have this 3D printed kidney, na? There was a software patch required. I downloaded the patch. It is now upgraded. Your urine will happen correctly now." So this is what is going to happen. Our knees are getting replaced. Everything will get replaced. Don't worry about it. Everything will get replaced. So, physical AI, which is going to sense, we had so much talk about companion, but this companion is going to be ubiquitous. Your shoes will tell you how many steps, everything, what you did, what you didn't do. And everywhere we are going to have integrated agentic AI in physical form. We are gaga about the power of AI. Most of us know how powerful AI, but I will still give you glimpses of trying to understand how interestingly and good it is. People in 2019 or before collected data of all chemical reactions. They changed the names of all the elements, made it A, B, C, D, A, B, B, numbered it, and gave this to AI. Once they gave this to AI with the simple query, now connect these elements which I have renamed, renumbered, based on the knowledge of these equations, and put them closer to each other, which is clustering, in a tabular form. Can anybody guess what it produced? It produced the periodic table, something very, very close to the periodic table. And all of us know that Mendeleev's periodic table is probably one of the most inhumanly ingenuous representation techniques, scientific discovery techniques. And can anybody tell me where he got the inspiration from, and which is the only other table which has got that equivalent power? And that is where this man Mendeleev walked 2,000 kilometers from Moscow to St. Petersburg because he did not get admission in Moscow. And which is the only other table from which he drew inspiration? It is the Paninian grammar table. Like you form new words, you form new elements. Like you form new reactions, you form new sentences. That itself, the Paninian grammar is, people tried to find the optimal grammar table, and it took days and days of optimization to reach something close to that. Here, but just by doing 10,000 training reactions on a 50 class model, they were able to predict organic synthesis up by 97% accuracy. How much of experiments is going away? All those who work on materials, structure to function, having few elements and data on structure function, using this new concept of graph neural networks. Please do not trivialize the neural network architecture. I said regression and all that. It's very, very sophisticated. It has got the knowledge and brains of lots of human beings have produced remarkable architectures, of which this graph neural networks is a fantastic architecture which is predicting function from structure without running experiments. This is our work where we are predicting the properties of aerodynamics, including in the chaotic region. Here's something of ours, huge complex software. How do you summarize it? How do you encode it? How do you pinpoint root cause error? All that which was hours and hours of coding and work, after appropriate training, has now really become very, very straightforward. This is my student, PhD student, BTech student as well. He just took a camera, few cameras and a motor, took pictures, trained it, and he runs a company called SIGTuple in Bangalore, which gives you the same equipment and tests which Siemens and everything gives you at less than half the cost. In machining, in welding, in additive manufacturing, everything has become completely transformed. Robots we know. Today, John Deere gives you tractors for free. You don't need to pay for the tractor. But what do you need to give John Deere? Can anybody guess? All your data. All your data. They only want your data. They will give everything for you to free. Most of the medical companies come to India for data because the regulations are not strong enough. And then today, even that all this sci-fi stuff that you see. In 2019, a book was written by AI, completely by AI on lithium-ion batteries. At that point in time, it was the best and the most accurate book ever. This is the test which has now replaced the Turing test. The test is as follows. I will give you all publications and research papers up to a year X. And you have to predict for the next 5 years what will happen. So the first experiment was conducted. All papers related to thermoelectric materials was provided up to 2009. Just the papers were read, nothing else. It was just reading of the text. And AI was asked to predict the next important thermoelectric materials. It predicted 5. And all these 5 were discovered by human beings in 2012. So you can imagine that in 2009, if that technology was available as is today, then all those materials would have been predicted instantaneously. So taking cue from that, the Turing's test has gone away. Modern test for AI is as follows. I will give you all publications of research till 1899. Can you predict theory of relativity? Can you predict quantum mechanics? So that is the new challenge to AI. The new challenge to AI is, can you predict the future better than some of the finest discoveries that human beings have made? And that challenge is on. This guy, many of you know, he's an 18-year-old person. He collected from NASA publicly available data of 200 terabytes, created a neural network model, and discovered 1.5 million new space objects. 18-year-old boy in 9 months of internship. This is the democratization, the power that AI gives to democratize discovery. This is the most interesting thing. This interesting thing is protein structure. In all of our institutions, 1 PhD, 5 years of experiments, 1 protein structure. This method which got them the Nobel Prize, discovered 200 million protein structures and made it public, which is 1 billion human research years. This is Terence Tao, the greatest living mathematician. And he, these were the naysayers, AI. No, it cannot do what human beings does. We all say that. But today Terence Tao says that he has used it to solve some nagging problems that he was struggling with. All of you who are computer scientists know this great man, Ronald Knuth. In music, whenever we talk about a great person, all musicians, Archie, like this, will touch your ears, saying, or you talk about Guru. So Knuth is like that. Whenever I talk about Knuth, my hands are on my ears. He has done almost anything that a computer scientist could physically do. And he has now said that he has been able to solve, using Claude, cases of systems. So these are the top scientists at the edge of their disciplines. These are not chota-mota scientists like you and me. Chota and mota, So it is therefore not unnatural that Nobel Prize is going and will go to domain people along with computer or AI people. It is just going to happen. And this is going to be the trend. Unless these Nobel people figure out something else and give it to somebody who is bombing somebody, but whatever. Next is crisis for us. AI is now able to conceive of theory, develop experimental plan, create 3D printed instruments, collect the data, analyze the data, verify it, and continue in this loop till it solves the problem. So this is the plan. And based on this, you are now going to have in the next 3-4 years, all of AI, standard publicly available AI is going to be at postdoc level. It's going to be at postdoc level. And what are we going to supposed to teach? We should now be able to teach a student how to make the next generation rock in class. How to use this sort of training methods, making the rocket, designing it, simulating it, testing it. And that is the new generation of education. I put this example, we are trying to design a new GPU using AI. It's coming out very fast. People have already developed power electronics chips. Then even more fundamental. People are looking at data for welding, collecting welding, and finding out fundamental physics equations for welding automatically. In fact, they have found an alternative to Newton's laws of motion using AI. And therefore, complex systems, all our companies, this is the IBM chief, whose hand is on his head. They have lost 13% in a day because almost all of COBOL was automated. Next, AI is going to enter us. And that was the topic of the discussion yesterday here. Very nice topics of discussion here. So one is augmentation, companion, augmentation, it is helping me. Secondly, it is going to become part of me. So all of you whose brothers, sisters, children are going to give JEE exam, चश्मा पहन लेगा, आंसर तो ऐसे ही आ जाएगा. All of you remember how many of you have seen this asterisk in the Olympic Games? That comics, yeah. They're that magic potion and you win everything. So the second part is human as a system. It will take half your decisions. What are your decisions? Like Anima was saying, instead of husband replying, intelligently reply karna shuru karega. But wife can find out. Don't underestimate wife. The third is system now behaves like a human plus plus. So half your organs and body, everything is replaced. And you are now enjoying yourself. You say, "Arey, theek hai, enough. I have now taught something in class. Now I want to do Bharatnatyam." So it will make you do Bharatnatyam. Don't laugh. This is what is going to happen. It will make you do Bharatnatyam, play cricket. And all you are going to do is be a witness and observe and enjoy. So the whole holy grail of having achieved bliss is going to come in the next 30, 40 years. But which means your privacy is gone, everything is about you is known. And if you are scared about that, then it's a problem. If you are not scared about that, then it's not a problem. So today, understanding emotion, that was the topic a little while ago. Understanding biology. The question of whether AI can give you subjective knowledge. Knowledge about awareness. Knowledge about self. Today we are able to predict progression of mental diseases. So one human being was put on the ground, or was put on the table and asked to think. An fMRI data was collected, and from that fMRI data, sentences were produced, and it almost conformed to what this person was thinking. So what will we do with all this? All of our education, all of our technology development was all in silos. That is because we divided our knowledge. We did not know other things. And in all academic institutions, you will see two persons sitting next to each other, A collaborating with a scientist in B on a topic B, and the next person knows B. उससे बात नहीं करेगा, वो सब London, Paris. And this will happen. But if we look at all of transportation, healthcare, manufacturing, infrastructure, where multidisciplinary concepts are required, AI is the tool. It is the tool for us to use. Everybody is making urban observatories. One option for IIT Mandi is to make the whole institute as a living lab. Manchester, London, Singapore, all of them have the city brain. And then all this public safety and education, we are, after some time, none of us, we will become gig workers. Because AI will know everything. So today, you are saying, I want paneer dosa in 10 minutes, blink it, lay out. Ta, somebody comes. After some time, faculty members, I want deep learning with integer weights, how to train, on your app comes. Hey, jao, 4 baje se 5 baje tum wo AI ka sath, you assist AI to teach the students. So we will all become gig workers. Unless we know AI fully, we will become subservient to AI in education. So academic institutions need to evolve about how they are going to, and the struggle is on, about how students are doing assignments, how are we giving assignments, how are we evaluating them. And nowadays in the research papers, we have in our computer science group, we have this very interesting discussion going on. People have used AI to write papers. The conferences are using AI to evaluate those AI written papers. And then the conference committee is using AI to evaluate whether the papers were AI generated or the reviewers were AI generated. And that is also using AI. So the whole thing comes like this. Teacher gives you an assignment. Write in details about nuclear reactors in India which are working in this form. So somebody uses ChatGPT nuclear. So 30 submissions aa gaya on nuclear reactors. And then teacher says summarize every submission into one paragraph and grade it. Nobody has learned anything in this whole process. So how are we going to change education? This is a very deep and interesting and important question. And I'm coming up with a new mechanism of helping students, so we'll come up with something very interesting now. Legal, the whole of legality, how to understand case laws, how to understand, in India, has anybody of you seen a legal document of India, in India? 5 pages, 1 sentence. And whereas, and whereas, and whereas. Have you not seen? And whereas, is 1 sentence. So, legal analytics, even today, is an interesting problem in India. How to give the common citizen, because legal is so expensive. You know, either you fall sick or you have a court case against you. Both will reduce you to nothing. So, how are we going to, what about education, robotics? These are interesting things. Then come to social science. How are we going to make food? How are we going to make, is there a way to do end-to-end so that orange juice is available at 2 rupees? Can you solve this problem? We can. The amount of tools that we have. How are we going to combine engineering disciplines with medical science? Nobody, only now with the movement of AI, people are trying to model the human being as a system. Supply chain, climate change, rural development, and this is where we are good at. Indian raga music does not have a grammatical structure, as in the Western form. Even AI is struggling to understand. Because 5 people are singing Bhairavi, the experts know it is all Bhairavi, but to you it is all different. So what is it? Is it something beyond AI? So whether it is heritage, whether it is your inner self, whether it is language, literature, which is very deep and cultural, then comes limitations. Look at this. Look at this picture. How many pictures do you see? One you see 2 human beings facing each other, one you see a flower vase. But look at it very carefully. You don't see them together. They switch. They switch. Either you see this or you see this. Either you see this, rapidly they switch. Does AI look at it this way? No. Your first reaction at looking at this is that this is longer than this, but second look tells you no. AI will never make a mistake because it is measuring it. It will just measure it. Grandfather, when I was your age, I used to go to the market with 2 rupees, bring home soap, rice, milk, bread, ghee, face powder, etc. Grandson, Dadu, very difficult. There are CCTV cameras everywhere. Why did you laugh? Did you reason and laugh? You laughed instantly. When did this laugh originate in you? How does anger originate in you? How does love originate in you? How does attraction originate? How does repulsion originate? AI struggles. Not this, I'm saying all of this. This is generation gap, but you laughed instantaneously. Can we replicate Tagore, Hemant Kumar, Satyajit Ray? Today people are making music like Bach, Beethoven, you will fake has become the norm. There is more artificially generated data than original data in the world today. The total amount of AI generated data has exceeded the total amount. That is becoming a problem in AI training because AI is now being trained with AI generated data. And obviously, your wife is talking to her friend saying, अरे हम देखा था ना वहाँ पर जो एक फ्लावर वाज था, very nice flower vase in that shop. You are sitting down opening Google, वो WhatsApp में बात कर रही थी, you have opened Google and flower vase का advertisement आ रहा है आपके पास. Firstly, WhatsApp is Meta, your tool is Google, your wife is talking to her sister, and you are getting this advertisement. Have you realized that how everything about you is known? Everything about you is known, but they are taking their safe AI is that you should not know that I know everything about you. Ullu banana. Look at this. These blue lines look tera mera, but they are straight. If you measure it from end to end, you will see it's all straight. Which means that we have illusions. These illusions are because of our sensors and our model, our neuronal interaction. AI will not have this mistake. It will just measure and correctly tell. AI does not see what we see. Therefore, because AI representation is different from our representation, it's not identical. Therefore, if I take a picture of a pig and I change only 30-40 pixels, I can make AI predict it's an airliner. But to you it is a pig. Which means that when your AI is crossing the road, the signal is red, I have adversarially attacked AI. By changing 30-40 pixels, it will see green. And dhadas. So AI can be attacked, and if human beings can have illusions, AI will have illusions. And you can make sure that you can enforce it to have illusions. You can attack it. then this is our own people who have found out thing. So making AI understandable, the decision making of AI understandable, explainable. Now this is all very good terms to use. I will tell you the difficulty of explainability in a very short example. You have gone to a doctor and your father has a problem, heart problem. So doctor has done thousands of tests, and your doctor who referred to this heart specialist asked that doctor, what happened? He says in that artery, that pathway, that is happening, this is happening, etc., etc. Mumbo jumbo to you. That doctor understands that doctor. They ask you, what happened in my heart? बोला आपका खून में थोड़ा fluidity है, कमी है. This is explanation. Whom are you explaining? Because you have to explain it to a person of that knowledge. AI can explain to another AI by just sharing the model, by sharing the inference. But how does it explain to a human being? You are going to lose information. Therefore, all explanation is a difficult problem, accurate explanation. Second is interpretability. How did you come to the solution? How did you come to the solution? In a probabilistically approximate method, how did it come to a solution? So as we have been discussing, all of learning is changing, all of work is changing. It is going to affect arts, sciences, engineering, technology, management. Privacy is gone. Security is gone. AI किसको धक्का मार दिया आपको? Nobody to blame. Autonomous car has hit a person. It brings in many more new computer science problems which are called morality problems. Morality problem is like this. An automated car is going. Now, there are two roads. In one road, 50 people are illegally crossing the road. The way you are going, there are 50 people illegally crossing the road. So if you stop and turn to the other road, then there is one person who is legally crossing the road. So if you go this way, you will kill one person who is legally crossing the road. In this way, you will kill 50 people who are illegally crossing the road. क्या करेगा ये? No. I'm giving you a hypothetical problem. I'm giving you a problem. This is an autonomous vehicle which is moving and it does not have time to do that, let us say. So these are morality problems. This is a simple version. There are more complicated versions. Then now you have answered JE using AI. Who is to be given? Your AI has solved the problem and it has earned money. Who is to be taxed? And then we all know, all of us, I didn't bring this up, because of data bias, algorithmic bias, AI seriously makes mistakes. Weaponization, liability, jobs. And then we use AI for what? My boss is angry, so I will make one AI tool which will focus on thanda air on his head so that his temperature does not go up. So that means we are using AI to solve problems of those who have plenty. Whereas 60% of Indian population own 3% of national wealth. Which means that there are enormous good problems to be solved, which will change the lives of people. If we academic institutions start addressing those problems, other than trying to run behind the richer people and solve richer problems of rich people. Problems of half the problems of rich people are artificial problems. So as we move to a society where automation is the norm, where we have got over the fear that there is a technology which can think better than us, which can create better than us, which is better than many things that we thought we could do, which was our prized possession, for which we spent years acquiring that proficiency, all gone in a day. At that point in time, how do we live? What is the society we make? This is what an academic institution should think about AI today. And that is the purpose for which I came to talk to you in this Himalayan settings, where we can really, really think about changing the way we use and develop AI. Thank you very much.
Thank you very much, sir. I think that is a splendid talk. And whatever you have explained, not only the topics that you have covered, the way you know how to engage the crowd, how to manage them, this was really engaging. Thank you very much, and big round of applause for our honorable speaker. I request Director sir now to come on to the stage and felicitate.
I think we cannot thank enough PPC, as he fondly called us, for this exciting talk. In fact, I heard his talk. He has gone even above in INE conclave that happened at IIT Kanpur. When I heard his talk, I thought that this is the apt talk for our faculty and students. And that's why I pursued with him that he comes. I'm really grateful that you came. Before we think, maybe one or two questions. SRC.
Yeah, ask ChatGPT.
I don't trust ChatGPT, first of all. I had a lot of questions to ask you, but one question I felt that I can ask in the auditorium. Can AI make a dead man alive?
Depends. Suppose a person has had a heart attack and has died, and an AI tool can come and do what even a doctor could not do, is one thing. So, if that person can be brought to living state by putting heart, lung, everything else to work, then is that person alive is the question. So that brings us to the question of what is alive? Who is alive? And that brings us to the more fundamental question of subjectivity, about whether AI answers the question of who am I? And the fundamental problem there lies in the certain set of undecidable problems. All our science, mathematics, not all subjects, but most of our mathematics is based on set theory. And in set theory, there is this fundamental question of the universal set. Everything of everything. And the question is, does that universal set exist in the universal set? For that is the fundamental paradox of science. That is the fundamental paradox of material-based knowledge. It does not answer the question of whether everything of everything is in everything of everything. It cannot answer. So that is the fundamental contradiction for which normal materialistic methods does not address this question of who is alive. Beyond this, you have to call me again for a talk.
Sir, if you permit me, I'd love to ask you a question. So, as you said, with AI, physical AI, I'm feeling like, suppose if you consider a human as a simulation, and if you consider that existing is also taking, like if you say AI is also a simulation, human is also a simulation, so how you, again, how you contradict or how you say this is a kind of, both are kind of, means how you address these things, like matrix comes into picture.
So, so her question is another important philosophical question, is that are we part of an experiment of AI? That means somebody beyond us has created this situation and we are all AI bots. And her question is, we are now impregnated with that intelligence to try and recreate ourselves.
Yes, exactly.
Have you understood this fundamental back healing question? That comes back to whether when AI was created, when we were created, whether that supreme knowledge of everything has been impregnated in us.
Yes.
In many philosophers who are realized has said yes. But when we have created AI, we have not impregnated that supreme knowledge. That supreme knowledge of our own awareness has not got into AI yet. Even if it has gone, we have not been able to realize it. Sam Altman was asked, what can AI not prove? Don't underestimate these people thinking that they are all businessmen and all that. They have enough money, they have everything. They are deep, deep thinkers. So when he was asked, what has AI not been able to do yet and may not be able to do, he says AI will not be able to prove Atman is equal to Brahman.
Yes.
Which means infinity and zero collapse.
Exactly.
Everything of everything is the same as nothing of nothing. In the sky of nothing exists everything of everything.
Sir, one last
Sir,
question.
one question.
Sir,
Sir, one last question, can I ask?
See, I know that there are many questions. Lunch time is there, and the vehicles have been ready for going to the Parashar. So there are many other plans are there. I apologize that you have many questions. Probably after the talk is formally ended, 5-10 minutes, you can walk along with PPC to the lunch and talk there.
And
Okay?
after dinner, we can have a big gathering.
Yeah. After dinner, PPC allows you to come and interact with him. And Aditya will organize that.
Only philosophical questions, no other questions.
Okay. Thank you. Thank you so much. It was so nice. And how many of you like the talk? So then give a standing ovation. I have a meeting at 2 o'clock. So I'm
Don't worry,
rushing.
don't worry, please, please, please. I ended on topics of interest to you.
That was great. Thank you so much.